All right, so let me get started. So before we get going, quick question, quick show of hands. How many of you are here for the first time? Just one or two? Okay. All right, so just backing up a bit, we've been running this for the last, I think at this point, 8 years now. So we started sometime in January of 2010, and we used to actually run it out of like the Barnes & Noble's Starbucks, and it used to be like 3 or 4 people, and we used to meet pretty much every other week, and then slowly we kind of ramped up. It was super popular and super effective. Sometime in I think 2013, 2014, we actually had a place which we rented. We used to run some paid programs, free programs, and a combination of a lot of those. But then, and then the interest died down, and now we picked it back up. For the last like almost a year and a half, we've been running regularly every week in one of the libraries. So please join us every week. Let your friends know. I think these sessions are now we are in the series of doing cracking the coding interview. Bunch of questions. Once we're done with it, I think we'll be done with this cycle sometime in June, and then we'll get together around that time and have like a feedback about the session, and also think about what to do next. Either we'll pick up one more series of cracking the coding interview, or we might actually start doing different sets of questions. So we'll figure out then. So with that going, wanted to see if anyone wants to share any interview questions that folks have been noodling with in the recent past, things that have been asked. Don't have to share the name of the company, but just a question. Like what kind of questions are being asked? I'm just curious to hear what are people working on.
So one question was we have sorted arrays, sorted arrays, and we need to merge into one.
That's actually the first question that we have today in the main session that we have is actually merging two sorted arrays. But given a bunch of sorted arrays, how do you merge them in, right?
Yeah. So there are like instead of 2, there are
n number of them. And
one rule was related to implement a circular queue.
Implement a circular queue. And what is the challenge with the implementing a circular queue? What's the complexity there?
Yeah. So basically, we usually implement using array, and we use modulus operator to use the empty space. We enqueue and we have some space available. So we need to have 2 pointers which indicates start and end of the queue in the array.
How many of you have actually implemented a circular queue using an array? Yes, no, maybe? Okay. So for folks who have implemented, the question for you is, there's pretty much one gotcha in that, which is around detecting whether the queue is empty or not.
Yeah, so I need to set, what I did was the starting point was set the pointer to -1, that both are at the same point, and we are equal with, we set the pointer to -1.
So the only gotcha for folks who have not tried it, definitely try it. Implementing a circular queue or a buffer is a pretty straightforward and a standard question. The only major challenge with that is the condition that actually tells you when a queue is full is actually identical to the condition that tells you when the queue is empty.
Yeah.
So how do you distinguish between the two is always interesting. There are different strategies you can use. One of them is actually to not let the queue be full ever. I mean, even though you have like n spaces, you only fill up to n-1. And then you call the queue full, so in that case you never reach that state, so that's okay. The other one is actually to code the values in a specific way that helps you. But it's actually fun to see what it is, okay? Any other question that folks have actually attempted in the recent past? Alright, so let's jump into the main set of questions. And one thing of course I wanted to make sure was, in case folks are taking notes, if you can just share it with me after the session, either in Slack or in email. I think I'd love to take them, compile them, put them together, and then share it in the group. Feel free to post it publicly as well. I think if people can take it directly, that's also fine.
Did you get a chance to post the video of last?
Yes, I did in a day. So I already posted in Slack and also on Facebook, and it's also on, I think I put it on Meetup as well.
Yeah, I see over there, but
April 7 system design. It is there. I already uploaded like a week ago, but I can check the Facebook group. That's probably easy.
Yeah, as some people may not know, I have a GitHub repository where I put complete solutions, unit tests, and notes on a lot of the questions. Not all of them, because I don't get all of them, but.
So I think I have that link. Just ping me that link again. What I'll do is I'll add that to the standard post that I put, and I'll put it. I'll pin it in the Facebook group so that people can actually.
There's a lot of questions out there. There's a lot of ones we haven't done too. There's like 50 up there.
All right.
Very clear.
Thank you. Absolutely helpful. All right. So let's get to the first question today, which is the question is essentially given two sorted arrays, and you're given two sorted arrays. You're given essentially an array. I don't know if the question is very specific about it, but you've got an array A and an array B, and assume that there is actually space at the end of A that can actually fit whatever elements, number of elements of B. Let's assume that this is like about 30 elements, and this is 20 elements. You've got like space to fit the 20 elements at the tail end if you need to. Your goal is to actually take all the elements of B and put them into A in such a way that the final A is a sorted array, which includes all the elements from A and B. The condition given is that A is already sorted and B is already sorted. So, how would you go about doing that? How many of you have solved this? All right, a lot more hands. I like it. This is good. All right, so how would you go about solving it?
Suppose clarifying questions like we have repeating elements, like we have A and B, let's say element 2 is repeated.
That's a good thing. So let me take a step back before we jump into the question. Right, I want to talk about how would you approach a coding interview question, whether you know it or you don't know the question, you don't have any clue. So the interviewer walks in and says, "This is the question. Go solve." Right. So what is your approach? What are you doing? So again, like how we did last time. So there's a bunch of stuff that you can do before the interview, which is essentially learn the algorithms, go through a bunch of questions, build your own figure out what you want to solve, figure out what are the different types of questions you want to practice, and all of that. But then once you're done with that, let's do the during interview. This is what is more fun. So during the interviewer is actually giving you an abstract question. Now what?
Usually, you understand the example,
Okay, I like that, but I'm not sure if you remember the format that we had, like the structure that we followed last time. The pattern is roughly the same, so let's actually go with it. Number one is, do you know what question it is? Is it a coding question that expects you to produce code? Or is it a question that expects you to problem solve? Or is it a question that's actually trying to get you to test your ability to, like, do you understand data structures or not? And things like those, right? So the questions can be in different categories. Even if it's like a coding interview or a problem interview that's given, like you're given this question saying, if I were to ask you to, given an array of numbers, find the third largest number from this list. Or find the nth largest number from this list or something, kth largest number, right? Now, for such questions, what do we know? What is the goal? Is the goal to get you to write code? More likely than not, because it's a coding interview. But what is the core goal? And I don't think the interviewer will share that with you right off the bat. I mean, some might come and say, you know what? I'm actually more interested in your ability to actually crack the problem. This is a hard problem. Let's figure out what it is. Sometimes the puzzle or the logic is so complicated that I'm expecting you to solve the problem. And not really code it. The coding is something that's secondary, and as long as we can, and most questions like dynamic programming, that involves dynamic programming or some sort of like maze traversal, the problem solving is the big deal. Once you've solved the problem, once you've got the edge cases, I think after that writing a code for like breadth first search or a depth first traversal is like just writing 5-6 lines of code. You've got a stack, you do a bunch of stuff with it, you've got a queue, you do like a few things, and that's it. Or dynamic programming is even worse. I mean, it's just 1 or 2 lines of code and you're done. So the code is not really the big deal there. What is really the bigger deal there is the problem solving. So I think the first thing I would do is like essentially I want to call it step 0 is like identify what the objective of the interview is. From the interviewer's standpoint, right? You're trying to figure out what does the interviewer want. And in most cases, it'll be like a mix of all the three, a mix of problem solving, mix of coding, mix of all of that. So go have that conversation to see what are we looking at. Unlike a design question where you have like very specific things you can talk about, you can say, are you looking for a class diagram? Are you looking for a sequence diagram? Are you looking for a system design? It's a lot easier. Here it's like, are you looking for me to write code? It's not a good question you can ask. It doesn't make sense. I mean, it's like, of course, yes, that's what I'm looking at. So you may have to start guessing what is this problem a complicated problem? So at this point, what do you think is this question? So given this question, given two arrays, and how do you merge them? What do you think is the goal here?
This is an algorithm question.
Algorithm, code, or data structures?
Algorithm.
So let me write down three things that I know I can think of as. So one is essentially I call it problem solving, which is essentially usually questions that are relatively hard, relatively abstract. There are enough edge cases and obscurities, so you need to use the right algorithm to solve. Then the next one is essentially, I'm going to call it like a data structure question, where you're expected to use some kind of a specialized data structure. So they'll need to use a trie, need to use a tree, need to use a binary search tree, something a little off the ordinary. Like even hash map, use of a hash map could potentially be a data structure question, like knowing when to use it, knowing how to use it. The other one is essentially just coding, which is essentially translating. Given an algorithm, can you translate it to code? Assuming that the algorithm like FizzBuzz is mostly a coding question. That's it, because the fundamental FizzBuzz question that you have, if you don't know what it is, look up. It's one of the basic questions that is like first asked. The idea is that's a coding question because the problem there's no problem to solve. The question is given to you. You just have to figure out like how to codify that into code. There is no data structure per se. I mean, you're just writing a for loop and you're done. So there's not much. Usually DS is combined with algorithms, and problem solving essentially is combined with problem solving leads to algo using a specialized data structure. So which leads to coding, and in some scenarios you start at the DS stage because it's not a complicated problem. As long as you pick the right data structure, you're good to go. And most common scenario is the coding setup. So this question, where do you think it is? Is it a data structures question, algorithm question, or coding?
I think the coding question is a fairly simple question.
It's not much in terms of problem solving. I mean, there is a problem solving. If you do not know if you have never done something like this, if you have never done merging two sorted arrays, if you have never done parallel walk in two sorted lists or something like that, this could end up being a problem solving question as well for you specifically. But I don't think the interviewer's expectation here will be problem solving. It is probably not a data structures question as such. It is using arrays, so there is no choice of data structures for you to make. I mean, it's already made for you. It is possibly an algorithm question because this walking two different arrays parallelly and figuring out, there are some gotchas that you have to take care of, which we can talk through that. And it is a coding question. So the expectation would be to actually write code, write the for loops, and what are the key things to remember key things to do for a coding question? Let's start with the coding question because that's what this most likely is. And then how do we attack a coding question? And then we can just work our way backwards as well. What are the few things to keep in mind when you're writing coding questions? Like best practices, tips? What language would you choose?
Your most comfortable language.
Say again?
You have to choose your most comfortable language.
What if it is something like Haskell or Lisp? I'm super comfortable with Lisp. Can I choose that in an interview?
It's up to you, so that you can write it one.
So it is a balance between, so the objective here is that you got to pick a language that most folks understand. Otherwise, you're going to miss the mark. That's one. So can I choose Python? Like, sure. Ruby, fine. Most high-level languages are okay because even if I don't understand the specific syntax of that, I would be able to understand what that is. So I don't have any issues if an interviewer, like a candidate chooses like, I want to do it in Ruby, and like, it's fine. But if you start choosing something which is pretty obscure, like Lisp or something else, like I have no idea what it is, and there's no way for me to even interpret what you're writing with all the parentheses. There are enough weird languages out there which are super specialized. I think there was one which was somebody introduced me to. I think it's called Bifunge. It's a spatial language, as in you write it as a matrix of letters, and then the instructions actually have to walk through the code in some graphical format to get to the thing. It's like, I have no idea. You want to write this code in Bifunge, be my guest, but chances are you're not going to make it through the interview, because if I don't follow you as a candidate, then the interview is actually not going to end well for you. So it's up to you, all right? So pick a language that you're most comfortable with. You don't have to pick a language just to prove a point. So do not just pick Java because that's what everybody does. Or if the company is working in Java and you pick Java up and you're uncomfortable with it and your syntaxes are all over the place and your you're not able to get to you're not able to express yourself freely with that language, then that becomes a negative for you as well. So there is a little bit of a walk in terms of what you need to do. As long as you're picking like C, C++, Java, maybe Python, maybe Ruby, I think it's probably good. If not, you'll be in for a little bit of a surprise. Again, depends on the company. If the company is specialized in, I don't know, Verilog or something, then of course you have to use specialized language for that. All right, so that's on so picking a language is that. Next is that most interview questions that I know of in the recent and now is like people tend to use some sort of a whiteboard-based coding technique. So the interviewer gives you a whiteboard marker, go solve. So what I would recommend is essentially visually partition the whiteboard into spaces that you want to deal with. Like so one of the things I would normally recommend is, given your entire whiteboard, I would usually cordon off some area where I'm actually writing the test cases, so that I can just solve it separately. So that let me just do that, and I'll mark out the test cases and I'll just write them somewhere and keep it that way. If I have any questions, I'm going to write them down somewhere in the bottom. And then this space is for me for coding. And when I'm coding, I want to start top left and then work my way down. Most folks may not be able to reach all the way to the top. So as high as you can reach, if you're as short as me, then I don't think I want to go all the way to right on the top of it. I can probably skip a couple of like 6 to 10 inches from the top and start from here. As high as I can go, where it's comfortable for me. So I would start coding somewhere here, and essentially I'm looking to actually partition the whiteboard into 2 or 3 columns and start writing the code. When you're writing the code, write code with, you can't insert a line in a whiteboard. It's hard. It's impossible. I mean, there's no good way to insert it. So generally leave a little bit of a space. Be cognizant of where the interviewer is in relation to you. If the interview is like a small, tight room and the interviewer is like just this close, then your font size that you write can be different. If the interviewer is like another foot back, then you need to write a little larger. So be mindful of where the interviewer is and make sure that you're writing as big as necessary. And what color do you use? Marker. If you have multiple colors available at your disposal, what color do you use? Black, blue, red is terrible because I cannot see red markers at all. Every time a candidate picks up red, you can see it because you're right here, right? So when I write something, I can see what I'm writing. But like 2 feet back, there's absolutely nothing I can see.
I try to usually write it. I'll write comments in green and code in black if I can.
Yeah. So if you have multiple markers available to you, you can make a visual impact by actually writing in different colors and all that. That may not be as relevant and necessary. The primary objective here is to make sure that what you're writing is legible. So I would pick a color that is actually reasonably dark. Blue, black are pretty dark. Green sometimes okay. I would test the marker, make sure it's actually working. If not, let it go and then pick a different one. What would you do in case none of the markers work or they're terrible? Then you probably have to do the best of the worst and go for it. Or you could ask for the interviewer to see if you can actually, is there a way we can get a different marker? Actually, I wouldn't even, I would even recommend like carrying your own marker with you. Not a big deal. I mean, if in case stuff happens, you're like, yeah, I have a marker in my backpack, let me just do that. I mean, that's just, you can do a whole bunch of different things. I would prefer not to use your own marker because most companies have their whiteboards in a specific form, they clean it with some specific liquid. Sometimes if you use like a super dark marker on it, it actually leaves a stain, it doesn't work, so you don't want to do that, that's your last choice. But in case they have terrible markers, nothing is working, bring your own marker. I mean, it's not that hard to do, and just do that. Like as an interviewer, I actually carry markers with me because I know that I don't control the whiteboard, the room where the interview is going to be set up. And my recruiters usually do a good job of actually going and making sure that the room works, the marker works, and everything else. But off late, we have recruiters who are not in the same geography. Our recruiters are elsewhere. I mean, the recruiter does not have to be in the same city as you are. So because of that, sometimes we have scenarios where the whiteboard is not set up, or the room does not have like a marker or an eraser or something else. So to do that, minor things. So done with that. So now we've written all of these things. So leave lines as you're writing code. Make sure that you have some line left, like a little bit of gap here and there, because the more when you need to insert, things, you might want to use that as an opportunity to then you can squeeze things in, you can actually just scribble stuff in minor things. Specifically where there are blocks of code where you want to come back and write, like for example, here's where my variable initialization is going to be. I know I'm going to add more variables later, so I'm going to just leave the initialization right up there, a little bit extra space, and then I can just go on. Things like those, like very small tips and tricks there. Done with the coding, finish that, finish this. As far as possible, try not to erase, because it's super hard to follow along as an interviewer when you keep erasing and going ahead at it. It's very difficult. So it's okay to reset, as in if I've written something and you know what, I don't like this, I want to start all over again. That's okay. But if you write something and then erase it, write something else again, I think that's just jarring. You had a question?
One thing I would say is, that this came up for me too when I was interviewing, is if you're going to move some code, like erase it and put it a little lower, always write the 2 before you erase the beginning, because you will forget what you've erased.
Yep. If I want to like move a few lines of code down,
Always write.
don't erase and then write.
Right.
Write first and then erase, because if you forget, then you can do that.
Which
But
you will, because-
alternatively, you can also draw an arrow and say, I'm going to put a block of code here. There are a few strategies, but try not to do that. So these are like minor tips, and the more you work on a whiteboard, you'll probably start recognizing these patterns, and you'll start seeing how these are like common failure modes that I see. So
Is it okay to insert variables later? Or I see somebody suggesting that you should have all in pre-planned, right? Or can you insert variables later?
So let me ask you this question. Okay? So for example, if I ask you, if I'm asking you to write code for some algorithm, which requires you to keep track of a variable, and you didn't think of it right out the get-go, right? So you're going through the whole process, and I'm telling you, how are you going to handle this case? Like, oh, I'm going to have a variable that actually tracks whether the scenario happens or not. Now you need to go back and insert it anyways. So in general, the variable, like adding a variable, that's how you think logically, right? I mean, if you already know the top variables, then you should just do that up front. Like, I know there's going to be A, I know there's going to be a B, I know I need like index variables for certain things and whatnot. Some of these things we can do it inline, but most of the algorithm-specific complexities will usually emerge later. So I wouldn't actually penalize you for not having those variables up front. I mean, it's that, or you go through the whole process of algorithm definition first, and then now you have all the variables. Now you go say I have variable 1, variable 2, right? I mean, I think that's, in my opinion, is a waste of time. So I would prefer you do that runtime, like figure out the variables as you go, as you're writing the code. Okay.
Sometimes the analysis take too much time, and you have limited time to writing code. Is it okay, like I put comments to say that, let's say, check the boundaries, like initially at the beginning of the code, and then do the majority work first, and then if have time, come back?
That's a fantastic suggestion. So when you have, I was just talking about code writing at this point, not code organizing. So that's the next one to catch up. So when you're looking at code organizing, right? So one of the things you want to do is like, I'm defining a bit vector, and I want to initialize it all to true, for whatever reason, right? That's what I want to do. And how do I do that? So I'm just going to say, init all to true. And I'm just going to leave 2 lines over there, and then move on and write the rest of the code. Because that is essentially a stupid for loop, where I'm just setting bit vector of I equals true. That's all I'm trying to do. And that 60 seconds I'm going to take to write that is a waste of my time. And I don't think the interviewer is going to gain anything meaningful with that, me writing that 1 line, right? And so that, in certain scenarios, what you can do is you can defer some of these things, like setup, cleanup, and even detection. I need to find the first first false bit in the bit vector. How do I do that? I can probably just say that's what I'm going to do, right? You can abstract it out as functions and code the functions later. You can abstract, so certain things that people do is they either leave space like this, or they actually call a function. That will simply say, like instead of writing it in text like this, right? I would just say init bit vector and then just pass the bit vector to it and call it a day. So that way what happens is that I don't have to write code, I'm just writing self-documenting code of sorts, and that function I can write later. And if the interviewer has a problem with interviewer suspects that I don't know what I'm talking about, I should say, can you actually go write that function now? Because I want to see what you're, I don't believe you or something. And that's one. The other case that have happened in my interviews at times, when the candidate has actually come up and has actually delegated the problem to a function, which didn't make any sense. I mean, if the goal for you is to find the k numbers or the top k numbers or something like that, they would write a function that says, all right, you know what, I'm going to get the input, take the input, I'm going to write a function later, we'll defer it later, to actually find the top k numbers, and then I'm going to print it out later. And they would spend a lot of time on the input and the output, and they'll delegate the meat that I really want as a function. And I'm like, no, that's not what I want. So can I actually, let's focus on that function now. I don't care about the input, the cleaning, the dedupe, and all that. That's not required for me. And so what are you going to do elsewhere? Like, I'm going to dedupe them. Like, let's assume that given the data is like already clean for you. So we try, as an interviewer, try to focus on, I want you to focus on what is the most important part of the problem, and what actually demonstrates your problem solving ability, your command of data structures, and the algorithms, and your coding skills, right? So abstraction and or like breaking it out into functions, or adding comments and leaving it out there, that kind of makes sense. Done with writing, you've written code, and preferably don't erase blocks of code as much as you can. You're done with this. Now what? Done with coding. You've completed the code. You've done everything. What next? Absolutely test. Test with what?
Examples.
Which example inputs? Well, we wrote the test cases here.
Yeah.
Do them first. We wrote the test cases, right? We went through the test cases. We actually kind of worked with the interviewer to figure out what the test cases were, right? We wrote all of those. So these are the golden test cases, like the test case that the interviewer has given. Your code has to work for that, right? I don't care what else it works for. If I tell you that if the input is 1 and output has to be 7, and I've told you what the algorithm is, if your code works for every other case, but doesn't work for the case I've given you, I don't think it's going to work well. It's not right. I mean, minor bugs are always possible, but you don't want your code to fail for the input that I've given you. That's the one. And then all the inputs that we've discussed so far, just making sure that it works. As you do that testing, that's when I would recommend using a different marker or a different color, so that you can actually start writing down what the variables look like and things like that. One of the techniques that I've seen people do, which this is where you could go overboard and actually mess up, is I know people who actually write the variable names, like I, 0 is 1, 2, this is the state of the array, and they write this matrix thing, how you learn in school, when you're trying to solve for like this is the for loop. So if I were to say FizzBuzz was the question, I don't want you to write like, I is 0, 1, 2, 3, all the way up to 99, and then say condition 1 true, condition 2 true, condition 3 true, and then walk through each one of them. That's not helpful to me, right? So I don't think this matrix structure makes sense unless the question demands it. So there are a few strategies we can use. We'll try some of those in this, but go ahead.
I would say to only do that too if you're used to doing those charts.
Even if you're used to doing those charts, so far I don't think I've seen any interview where I found that useful or effective.
Depends on the question. The more complex the question, the more necessary that is.
For dynamic programming questions, building the table makes sense, but that's not in this format. That's not an iteration. That's not the way. The way I see this iteration being listed out in textbooks is for someone who doesn't have any clue as to what the algorithm is. This is the one that helps you learn the algorithm better, because you're looking at, this is like sort of the like inspect variable or watch variable kind of a view, which helps you learn the algorithm for the first time. But that's not the plane of operation that you and the interviewer have, right? The interviewer already knows the algorithm. The interviewer already knows what to look for. So as an interviewer, I am looking for, did you get the common gotchas here? And what are you solving for? So if you, as a candidate, know what the algorithm is, if I, as an interviewer, know what I am looking for, this is an overkill. I have never seen so far where this has actually helped me. Like dynamic programming concept helps, like where that matrix helps, because that matrix is like the data interchange between you and I. If you fill that matrix correctly, then I know that you know what you're talking about. If you make mistakes in that matrix, I can say, recalculate this column, recalculate this point. And then we can figure out, I can actually zoom in on where you're actually making a mistake and why you're making a mistake, and identify why you're wrong. Or maybe your assumptions are different from mine. So that helps me. But not this sort of this variable thing, which is like what you read in textbooks, has never helped me. So, done with the testing, everything is done, all right? So I'm so far assuming the interviewer has not interrupted you. But we'll come to that, but assume what next? Go ahead.
And so for the test cases, usually the interviewer will give you examples, so I guess like before writing code, it puts there, right? So for other test cases, especially age test cases, do we put there before start coding or after that?
I would generally do that after I code, because I don't generally believe in, so there are two types of test cases. There's black box test cases and white box test cases. Black box test cases are the ones where I'm looking at it as an abstract problem, and I'm trying to solve it. So if you were to tell me that, write a program to compute factorials, right? I'm going to ask questions saying, so what about negative numbers? What do I do? Do I return 0? Do I return negative? So as a part of my requirements clarification, I've gotten those test cases out. I'm going to write them down. Boundary conditions, like what happens if the number is large enough that it actually overflows? Like how big can I go? Because I can easily sense that it'll overflow. I might actually start with that saying, up to 1,000 is what you need. So I'll compute a fact of 1,000 and call it a day. I'm assuming 1,000 actually doesn't trip, but if it does, then I'm screwed anyways. So we'll figure that out. But that being said, there are certain test cases that only will come up when I'm writing the code. And as I write the code, depending on the algorithm I've chosen, depending on the data structures I've chosen, I will have a few scenarios where I suspect my algorithm might fail. And those are the ones I will add afterwards. So those would be my white box test cases where I look at the code, I'm looking at the common boundaries which are actually code specific. So boundaries are usually based on data input, and certain boundaries are based on how you actually do your algorithm. Right? So I would pick up test cases based on that after that. So usually for more complicated algorithms, that's how it will work out. So combination of both. So interviewer given test cases, your own black box test cases, and then after you've written code, your own white box test cases.
What I was going to say about the thing you were commenting on the chart or whatever, what I found to be more useful usually is, especially in linked lists, linked list pictures are really valuable in my opinion, because there's all kinds of pointers going in all different directions. So for a linked list question, I would always draw a picture of a tree.
Yeah.
With the
for tree, for linked lists,
yeah, with the pointers, and then what I'll do is sometimes use different colored pencils for each iteration to say, this is going, this
totally
was
works.
green, now it's going there.
Totally works.
For an
Absolutely.
array, I would usually just draw the array and put arrows, as opposed to that.
So linked list is as a part of your how you, so the Uber message, or like the underlying message, the fundamental message here is that you need to use whatever mechanism that you want to help you solve the problem. That is like fundamental. And then you also want to have as much information and detail here that helps you communicate with the interviewer effectively. So if I have the linked list drawn out in a specific format, and I'm saying that if the goal was to reverse the linked list, right, then I'm going to say here's like link 1, link 2, link 3. Here's what the value is. I do all the graphical view of pointers, and then I'm going to say in step 1 I'm going to erase this. I'm going to reverse the pointer. In step 2 I'm going to do this, and you can do that. Now if you do it all in the same color, but you've done it sequentially, the interviewer can follow along. If you can actually do it in different colors or different, like you number the step, like step 1 I do this, step 2 I do this, it will be a lot better. And it'll, even if the interviewer is busy checking his or her email while you're actually doing this, they can catch up with what you're doing quickly without having to get confused. So that's something, okay? So code organization, I missed one fundamental aspect of it is, what is the first line of your code? The method signature. The method signature. Even before you start checking, right? It is the method signature, the input and the output. Like, what do you want from me? And that's like, that has to match the problem statement you're given. That is the contract that you're trying to solve to, right? What is the last line of the code?
Return.
To return value, to return whatever it is. Or if there is no return and your goal is just output, then you need to print things out. Just one of the checks that I do as a part of, or I ask people to do as a part of their activity is to make sure that they're returning in all circumstances. Like, you have all the if, then, else branch conditions. You need to make sure that you're returning everywhere. Like, most common one is when people are supposed to, like, tell me if this array is sorted or not, right? So they would go through all the magic and return false every time it's not sorted, but then they forget to return true in the end. Which is, I know what you mean, I know how, and I don't point it out, I wait for you, what? Walk through a happy case, let's find out what happens. And about 10% of the people still don't figure out that they need to return true, because they go through all the falses and it's like, not false, not false, not false, not false, done. I'm like, okay, so when will it return true? I'm like, oh, I forgot, I need to do that. Happens, nothing, again, at an interview, I know people are a bundle of nerves, so I totally understand. So I'm not trying to penalize you for missing that one thing, but those things do happen, and you don't want to be in that position. I can easily see how people get worked up with such things, like, oh, you didn't initialize the variable, you didn't even create the variable, you didn't set it true, or you missed like the not condition. People actually forget, like, instead of like, while true, they might write while not true or something like that. And that's because you run it once, it will not run. You know what it is, you'll fix it. So I know that you'll do it. But it's just that at an interview when people are actually nervous, they may make these silly mistakes and they may not catch it. I expect you to catch it as a part of your test cases, but if you don't, then that is definitely an area for you to grow, but I don't think it torpedoes your interview. So we're done with the test cases, done with this. What's the next thing? First is signature, okay? And at some point of time, you would actually check the return. And immediately after you're done with this, after you're doing the message signature, you do what? You validate the inputs. And I call these like the gate checks. So essentially, you protect your function down underneath the covers from actually failing by checking your inputs, like my array cannot be null, the value has to be positive or something else. Those gate checks happen in the beginning. You don't have to go to town with the gate checks. Like you don't have to say, I'm going to check everything in all scenarios over there. Just demonstrating the fact that you know gate checks need to be done is adequate. So do one gate check saying if array A is not null, array B is not null, then you're good. And then you just mention that if there's any other validation I need to do, I'll add it here. We can come back to that later, that's not as important. The fact that the goal here is to communicate to the interviewer that you're thinking about entry input level validation. That's about it, right? And then there's the meat of the code after that. So this structure is something that is not natural to folks. I mean, this requires more organization, it requires more thinking, it requires deliberate follow through. And if you're, depending on where you are in terms of in relation to the interviewer, I mean, interviewing is also, there's a little bit of theatrics to it, so you're trying to make sure that if the interviewer is sitting here or if there are a bunch of interviewers, you don't want to have your back to them, so you need to find a way to figure out how you want to stand, where do you want to, try to face the interviewer when you're talking to them, understand what they're trying to say. Because the goal here is to take the interviewer with you along this whole journey of figuring out what the problem is. I think you have a bunch of chairs in the corner there. So that's the objective, right? So that's all I had for the coding with one. Go ahead.
The one thing I would add is that that happened to me with this very problem, actually, believe it or not. But if you get stuck on a certain part, I would just put a comment and then come back to it after that. Because otherwise you psych yourself out on the part that you're really focused on, and it could really throw off your whole
So you need to have a way of figuring out when you're spinning. Right? When you're not able to get to an answer, you're trying to. That usually happens in the PS or the data structure algorithm phase, not usually in the coding phase. Like in the coding phase, if the expectation is that I need to do something, I need to set everything to true, I need to print everything, I need to print a matrix, I need to reverse something that's very well understood part of the logic, then in most cases what you can do is you can actually just do this function thing whenever you're stuck and say, I'm going to write a function that can reverse this thing for me. Like one of the questions was, I think this was reverse the words in a string, not the letters, but reverse a word in a string in place, right? So the problem solving element of it is that essentially you reverse the whole string once, and then you reverse the words specifically, just pivot around the words and figure out where does the word start, where does the word stop, and then you go for it. That's the problem solving aspect of it. Now when it comes to coding, you're actually coding essentially what you're coding is how do I actually invert something from index I to index j, and that's all you're trying to do. Now if in that particular scenario, if you need to do something, you can probably abstract some parts of it. The actual meat of the question is that reversing from an arbitrary index to another arbitrary index, so you can't just abstract that away, but everything else you can probably abstract away. Figuring out where the word ends, right? I don't know. Is it a space what ends a word, or is it like a full stop ends a word? What do I do, right? You can kind of make some assumptions, or you can make some abstractions there. So, specific question aside, I think the goal here is for coding, if you get stuck, if you're spinning, try to move on away from it, abstract that area and go on. But if you're actually spinning on the meat of the question, the basic line of the question, then you are kind of out of luck. There's not much you can do. Keep exploring different options till you come to something. So that's the coding. Let's talk about data structures and algorithms. So what are the additional things that you might want to do for data structures and algorithms? So that happens before this, right? This is the final step. This is the coding step. Before I code, I still have to do the test cases. This is the input, this is the output, that's what is expected of you. Now you need to pick the right data structure for this. This may not be the right question for it, but there is a different question later in today's session which actually covers that for us. So we can figure out, we can pivot a few data structures. How do you how do you pick the right data structure?
Evaluate pros and cons,
Mhm.
evaluate speed, space.
See what we're trying to solve.
Based on the problem.
That's the key there. So I would like to, and later in today's question, I'll try to reiterate and point out the area when we look at that. What I want to do is like, I want this data structure to do this. I want a structure that can hold a bunch of integers and at will can give me the smallest number in the lowest possible cost and whatnot, right? So and that what data structure am I describing? It's a heap, right? So and if I actually talk about like, if I want a data structure where I should be able to add elements to it, and I should be able to retrieve the elements in the same order I added it, so that I can use it for something else later. Is a queue. So in these scenarios, right? These are trivial examples, so obviously you wouldn't even think about it this way. The moment you think of the problem statement, you know the queue as the answer. But if I actually talk about like I need to do this and I need to do that, you should be able to, like the requirements should be able to tell you what data structure it is. And in later session, I think I want to specifically, I'll try to not name the data structure and I'll try to name the requirements, and let's see if we can actually get to the data structure, and we'll get there. So that's what the data structure piece does. And data structure is not something that you do in isolation. It is almost always a part of the algorithm, because there are certain algorithms which actually require you to store the data in a specific format, hence you need a particular data structure. A different algorithm will not need the same requirements. So the requirement from how you organize your data will differ based on algorithms. So algorithms and DS, they go kind of hand in hand for that reason. Now comes the uber problem solving. Of all of these things, the toughest is problem solving, because you need to understand what category of problems does this thing map to. What have I done? Like like this question, what does it look like? Can anyone say what category does problem match? So coding, yes, but problem. What category of problem? If it's from a problem solving standpoint, we said it's a super trivial problem to solve because the algorithm is straightforward. But what problem? What kind of problem is it? Can you name another problem which actually follows a similar, which will require you to solve a similar thing? Give me other interview questions or other fundamental questions that you have solved, which require merge sort. What else? Merge to linked lists. What else? We have heard the merge to linked list problem, right? If you know how merge to linked list works, you should be able to solve it roughly with the same algorithm. The boundary conditions are subtly different, but that's always the same thing. Merge sort involves you merging two sorted arrays at different points of time. So this sounds like a merge sort problem. So yes, what else? What other interview questions have you seen? We have solved one in the last, I think, 3-4 sessions ago, was one around one of Amazon's standard interview questions. If you Google Amazon interview questions, then it'll probably be there in the first few pages, is you're trying to figure out visits. Like people who visited on Christmas and New Year's. Like I have a data file which contains a bunch of customers, and you need to find out who visited on New Year's and Christmas. And it's intersecting two large lists is the question. And in one of the solutions for that is essentially involves sorting both the data sets and essentially identifying, like trying to walk through both the data sets together to identify the common ones. Very similar pattern, very similar approach. Now, normally speaking, for such interview questions, when you see a question, you should be able to immediately have like 3 or 4 viable questions that you've solved which are in and around the same area. Like if it's an exact match to something else that you've solved and it's like just a variation of it. I mean, someone says instead of 2 large arrays of numbers, they've said it's 2 large arrays of strings. I mean, it's the same question. If it's an exact match or it's a simple match, then I think mostly the focus is on coding and not on the other areas. But if the question is more around it's something abstract, something requiring specific data structures or something, then it's probably a problem-solving question, right? So that is done. So we're done with so we kind of walked through a bunch of the stuff during the interview. What do you do after the interview?
Where does the algorithm be on the whiteboard?
I generally don't. I don't recommend having an algorithm at all, because most likely your code should be the expectation is that we are proficient with code, and we should be able to express the code with the algorithm and code should be the same. Right? The way I think the way I can equate that is is something that if you're actually building something or you're drawing something and you're creative enough and you should be able to just do that right off the bat, with minimal outline-based design, you should be able to solve these questions. Given a 40-minute interview question, the algorithm aspect, there is no need to spell out the algorithm. You would actually use the problem-solving time to go figure out what the algorithm is. And that's it. There is no writing down of algorithm. There is no, if it's 1, then I will do this. If it's 2, then that. That algorithm thing is not spelled out. You will use the time for problem solving to figure out an outline of the algorithm, and then you should jump straight into coding. And your code should be simple enough that it actually, it's just a mapping of the algorithm. So that way, in your head you have the algorithm, you just map it. I would not waste time with algorithm. I have had multiple candidates ask me at different times saying, can I write pseudocode? The answer is, you can, but please don't. Because, yes, no, please don't. I'm actually looking for code. And let's jump straight into code. Like I don't understand what possibly pseudocode can help us here. Pick a language of your choice, go right into the language, I can follow along. I don't think there's if I have confusion about how you're using the language, then I'll stop you. I hate when people solve in Python, because most common problems that I see that people actually solve it in C, C++ with for loops and conditions. Everything has like one expression in Python, like an idiomatic expression saying like this dot colon open bracket exclamation done. I'm like, what? I have no idea what to do. I mean, which I think with Java, the lambda expressions and everything, and C++ has something, C# has something similar. It's making my life harder, but as an interviewer. But usually what I do in that case is like, fantastic. Now explain that to me, and if they're able to explain that whatever they've done, then that's probably fine.
I usually avoid like using languages like I'm a C# guy, and C# has a lot of link expressions.
Mm-hmm.
I'm not going to use that in an interview.
Try not to, because I don't think
it's
it
very
helps.
language specific.
Yeah. Or you could actually say, you know what, I can write a simple link expression for this, but I think let me solve it the bigger way, because that's more transferable, and I think I can express my thing better. And if the interviewer comes back and says, no, go for it, you should be able to. I mean, so. Don't mention it till you're strong. If you're strong at it, then mention it. Otherwise, don't, because the interviewer can call you on anything, right? So anyway, all right. So that takes care of this. What about after the interview? You're done with the interview. Everything is done. You've shook hands. You've gone out. Now you're actually on the way. You're on a cab back to the airport. Headed on a plane back to your hometown or whatever.
Before that, do you need to talk about complexity?
There are a lot of questions an interviewer can ask. So there's always going to be elements of time, and so coding, one of the biggest elements that people expect from algorithm and coding is your big O, right? So that is definitely a part of the conversation. Like big O is definitely one of the parts of the conversation. It depends on what the interviewer is actually looking for. If the interviewer doesn't ask, I don't know whether I actually go ahead and volunteer. I mean, if I'm super certain, then I will do it, but I don't know. I mean, I'm in my problem-solving interview, I generally am looking at space complexity, time complexity, and whatnot. Like for this question, if someone comes and says, "Oh, the time complexity for this looks like O of n," and the space complexity, and I'm not even looking at it, it's so obvious, let's not waste time stating it, then it's different. Because there are other interviews which will focus on that, I may not be asking for that. So, in most of these cases, you have to take a judgment call of whether you want to use it or not. Sometimes people actually are very aware of time and space complexity. So they use that as a sentence, like every statement of that, they'll just use that. Like for this thing, I can use an array, but I have to sort n log n, or maybe I can use a hash map, which is like O of n. So it doesn't sound jarring to me when they actually go through that process. Because to me, it looks like they're natively thinking about big O every time they do everything. And it's not artificial. But if they come back and make it like a very specific statement, saying, here, let me draw a table of all the big O's and everything else, it looks like they're trying to play to me when I'm not asking for it. It sounds very jarring. So a lot of ifs and buts. So done with the interview, somebody said thank you note. Thank you notes help, but not a whole lot. I mean, I don't think it makes it. I don't think of a single scenario where like a thank you note from someone actually made me say yes, or actually made me say no to someone. The thank you note sometimes doesn't even make it to me before the decision is made. So it sometimes happens after the decision is made. So it doesn't help as much, but I think it's always courtesy to do that, and definitely thank the recruiter for arranging it. All of that, because I think recruiting, the recruiters are under a lot of stress. They talk to a lot of candidates, and well, I mean, once you get a job, you generally try talking to the hiring manager and your team. You don't care about the recruiter. If you don't get a job, you scream at the recruiter and then you move on. So it's kind of a thankless job from a recruiter standpoint. So every little thing that you do, all the thank yous, definitely help. So I wouldn't stop you from that. But and I'm not sure if it actually has any impact on the outcome except making the world a better place. So of course, why not?
The problem with sending a thank you to instead of thanking the recruiter but not the interviewer, because you usually don't have his email.
Sure.
Asking for people's emails is tricky.
Yes, don't do that.
Yeah.
Don't do that. Don't add them on LinkedIn. Don't do that in an interview. Please don't.
I remember last week we talked about reflection, trying to review, write down the interview question, go home and review what you have done and how to improve it. And if you can find ways to improve it, do let the recruiter know and forward your view.
Yep. Yep. So if you in the interview you just went through the whole thing, you actually got like a suboptimal solution. You've written the code and everything else. Like it just didn't strike you that I should have. You know what? Maybe I could have used like a hash map and it would have saved a whole lot of things. You just didn't think of it. Super specialized data structure or something. You didn't think of it, and later you figured it out. All right, and later it's like just struck you, and it was like you take the time, reflect on the question, write down what the question was, write down what you did, walk through your interview, like just play back the interview, and then if you discover there's a better way to solve it, write to the recruiter. That's like, hey, on this my third interview with this guy, this is what happened, and I think it's like later it just struck me. I've had one scenario where where a candidate actually did not get to it was like supposed to be. I was expecting a hash map solution, didn't go anywhere near it. Only got to brute force, and it was just one small part of my interview. We did a whole bunch of other things, and I was a hiring manager, so coding was not even in my territory. It was not even something I was supposed to look at. But we were done with the interview, so I thought, let me just throw a coding question, and the candidate bombed. Didn't get to the right one, despite a bunch of hints. It was like the first interview after lunch or something like that. It didn't work well, and then about 30 minutes after my interview, after the whole interview loop was done, I got an email from the recruiter saying, hey, by the way, here's what the candidate said, and which was essentially, I don't know what happened, brain fart, I just missed it. Here's what I would have done. I don't know why I missed it. It's like such a simple thing. And later in a different interview, the previous interview and after interviews as well, his coding was fine. I didn't have any issues with that because I had enough data points for that. So I was super comfortable setting aside my personal observation, and relying on the other interviewer's observations to go get the decision done. I would have done that even otherwise, had the thank you had the oops, I made a mistake note. Had that not come, I would have probably made it. But it made my decision a lot easier and quicker. I was more compelled to actually set aside my thing, because more likely than not, it is this. Because it's very easy for me to actually dig my heels in and say, you know what, I don't care what he did. He probably knew the answer to your question. That's why he did well in your interview. For something as simple and trivial as this thing, he didn't know how to figure out that it's supposed to be a hash map. I think I gave him all the hints I could. I'm not convinced. I don't want him on my team, right? I could have easily done that. And hiring managers, actually, since you report into the hiring managers have a lot more say in the interview than other interviewers. So it's a judgment call. So for me, it was easier because the candidate had actually sent an email out later with saying, oops, I don't know what happened, but this is what is the right answer. So, well, if the person can come back with the right answer in another, a couple of days, you generally don't solve problems in 30 minutes or 40 minutes, in the real world. So if you're able to reflect on it immediately and get me that, I think I'm more inclined to do that, to set aside my own observation and use somebody else's observation in the interview loop. Now, if the candidate had actually messed up every interview on coding, or if mine was the only coding data point and the candidate screwed mine up, I don't think you coming back and saying, oops, I messed up, is going to redeem you. Not enough. But this was just enough for me to get there. So I don't see any downside of it, but I see upside of it. So if you actually are able to reflect through this, go and ask, see if you can actually reach out to them. So that's one thing on the post-interview. Another area where this actually helps is that you need to identify areas where you actually didn't do well. And you need to know why you didn't do well in those things. And in multiple organizations, they actually have, they keep history of your interviews. So if they know that you actually did a terrible job of asking clarifying questions last time, which was like 2 years ago, and now I'm giving another opportunity to come and interview with my organization, right? And I go read the prior feedback and I say, oh, this candidate actually does a terrible job of jumping into conclusions and making assumptions and doesn't ask any clarifying questions. I'm going to be watching for that in this interview. And you better start with asking a ton of clarifying questions. And since nobody told you the feedback, in person, nobody tells you the feedback, it's up to you to actually figure out what the gaps were. So spend the time, figure out what it is, mark it, identify where you've made mistakes, and then next time go try to rectify some of those mistakes. That's the strategy I would follow. All right? So
Is it okay to ask feedback?
it's okay to ask feedback, but I can guarantee 99 out of 100 times you will not get any. Why? Why don't you get feedback? Liability, okay? The companies are in the business of actually evaluating you to make sure whether you're fit for the job or not. And they're trying to optimize for the companies, like your success at the company. If you don't do well, you're out. And there's literally no benefit for the company to, companies are not in the business effectively of actually trying to coach you and make you better and then come back and that's what schools are for. That's all, and I would invest time on people who are already in the company and try to grow them better than to actually give feedback to the external folks. The downside is actually, the upside is very low, because even if I make you a better engineer, you would become probably even better engineer and then you go and join a different company. So I'm not getting much. Unless everybody tries to do this for the greater good of the economy or something, this is like a game theory wise, I'm actually shooting against myself. It doesn't work. And the downside is essentially that it gives you more opportunities to challenge. And it's just unnecessary conversation. If I were to say, you know what, you are actually terrible at figuring out array-based algorithms. What do you mean array-based? I know it. And I told the interviewer as well. The interviewer didn't get it. It's his problem. So why are you penalizing me for that? And it's an unnecessary conversation. We have already, I don't trust you, I trust the interviewer. So that's already established. And the interviewer said you're not good at arrays. That's it. Now, I don't want you to use that as an opportunity. I don't want that conversation again. That's what I'm trying to avoid. So I don't see any upside. I only see downsides. Now, few companies, what they have done is that they actually let the recruiters prime you up with more feedback. They would give you, here's the type of questions they ask, like most of what you're doing here, this background, how to present yourself, what kind of questions they may ask. So they'll give you a little bit of primer and insights into it, because it's in the recruiter's interest to make sure that you are prepped up to a level where you can demonstrate your true potential. So that's not, the goal here is to make sure that the interviewer can actually, so if you don't do well in an interview, it can be for one of two reasons. One is that you're really terrible, or two is that the communication just didn't work. And that you didn't understand what the interviewer was asking for, or you didn't present the right data. That you're a right engineer, but you didn't present the right data. Now, the recruiter's role here is to make sure that they are kind of cleaning up the communication in such a way that the second part doesn't happen very often. And if you're terrible, you shouldn't make it through, and if you're good, then you should make it through. That's what they want. And in order for them to do that, they will give you more guidance, hints, and tips. Sometimes recruiters will back channel feedback to you somehow subtly, saying, hey, you should do a little bit more data from design, because your design skills kind of came out weren't as strong based on your experience and whatnot. So they may give you some feedback like that, but it's not something. It's not by design. It's not concrete, and by design it's kind of directional and vague. So that is there. So that's one thing. The second thing, of course, is talk to the recruiters before, listen to everything that they have to say. They are interested in getting you hired, absolutely. So that's their absolute goal. So every help that they provide is meaningful. Do not just skip whatever they're saying, right? Don't gloss over it. Second thing is definitely listen to, even after the interview, even if it's not successful, the recruiters actually give you the right sort of feedback, because they are in the business of building relationships and expecting you to come back again later with them. And sometimes the recruiters move companies, but they can take candidates with them. So they may actually help you with a different company. If they were to move, they can probably work with you. So work with the recruiters always. Second, the other part of it is there are paid programs and like mock interviews that many companies offer, where they will actually do the same thing. They will walk you through the interview, identify your gaps and things like that. If you are flying blind and you don't know what you're doing, strongly recommend some of those sessions. There are a few which, unfortunately, I have not seen any. I have not been through any of those mock interviews myself, and I haven't seen the output from any of them, so I can't recommend any based on my feedback. But ask your friends, anyone who's actually gone through mock interviews, figure out if it's actually helped them or not, and go for it.
Because LinkedIn too, you can, I don't know if you want to create LinkedIn Premium, but you can ask for help and they'll hook you up with different people who can help you with your interview practice. Do mock
LinkedIn has this mentor program now that they've started for not for interviews in general, but it's like typically a mentorship program. But I think there's like Pramp and Gainlow and like all these companies, they take money, get you like connect with the right people. Some of it, I think there's one which is mutual, it just connects you two people together and then talk. I've heard super mixed reviews about it. If the other person is as terrible as you are, then I mean I don't know what. I want to be connected with an expert, not with another noob who doesn't know what he's doing, and I don't know what I'm doing. So what is the point? Me getting connected to some other guy who doesn't know what he's doing. So anyway, so that's something that is a little terrible. So I don't know. I'm just it can help. That is one. Then of course sessions like these. Here we are not doing individual coaching. What we're doing is more of like we're covering a scatter shot of all the topics. The big thing I want us to take away is focus on what is specifically like your roadblock, and that is something that we don't cover here, and that is like a biggest gap in like you could be here going through our sessions for like months at a time, 6 months, 8 months, and still not be successful in interviews because whatever is stopping you from performing an interview will continue to stop you. No amount of knowledge and learning is going to help you there. You need to identify what's stopping you, what's actually not making you tick at the right level, and identify what is the roadblock, and then eliminate that. So that is not this session. This session offers a ton of material, a ton of feedback, exposes you to a lot of these things, and actually gets you going. And if you're stuck with something, once you identify where you're stuck, we can help you unlock to some extent, and that because if you're stuck at something, probably somebody else is as well. So we can work through some of those things, but it doesn't help. We don't do individual ones, at least not yet. So till that time, I think you probably have to find a different avenue to go find out. Okay. All right. So done with the process. I know it took about an hour to get here, but I think this was. I just wanted to walk through the mechanics because that's something that I think will help us structure our class. Okay, so now let's get to the question. Alright, so the question is given two arrays, A and B, A is sorted, B is sorted, A is actually sorted till a point and after it's all nulls are empty and there's just blank space at the end of A, enough to load B into it. How do you actually solve it? How do you combine it? Go ahead.
Okay, this is a fairly straightforward problem. Because of the fact that you're merging into the same array, one stipulation is like if you had a third array to merge into, you could work from either direction. But in this case, you need to work from the back because you're putting stuff into the back of it. So your basic strategy is to start at one point, take the appropriate element, put it in the right place one by one until you get to the end. Basically. And in this case, you have to work from the back.
So yeah, very simply, I think that this is one of those merge conversations that we've had. Merge sort, merge to linked list, and things like those. Your question is like, let's solve the one problem of what do you think is going to be the last element? It's either this element here or this element here, right? It's one of the two. You know which one it is. So you should be able to go and say, let's assume this was this, so I fill it in. Now, what is this next element? That element is either this or this, whichever is greater, and then you can keep going. So that's the high level, and that's the problem solving element of it. It's pretty straightforward. Once you know what the problem is, it's pretty straightforward. If you did not know merge sort, if you did not know any of the merge algorithms, I don't think you'll actually conjure up this algorithm quickly. It's not easy, right?
The tricky part is when you run out of elements in one or the other. Right?
So we'll come to that in a second, right? So what happens if you actually are reading up all the elements, and do you ever run the risk of overwriting something that is here? Can I actually? Is it possible for me to be writing, since I'm writing from the back? What happens if I accidentally overwrite something that is already there?
You can.
That is already on the right side.
How do you know that?
Because like we are comparing the two elements, and if that particular from A it is greater, if you go there, and that spot is actually you can say it's free.
So without knowing too much in terms of specifics or
Here's
details.
one case is in the worst case, if all of the elements of B are later than all the elements of A, then you would put them all at the end.
So that's what I would say. So essentially, my goal here is the worst case scenario for me is if every element of B is like I need to inject them here. If that's what I need to do, then I can actually take all the elements and put it here without having to overwrite anything. So I don't believe that there's ever going to be any possibility where I'm going to be destroying information. So all I'm saying is that you need to have the intuition to start figuring out, like, here is all the failure modes, or here is all the boundaries, and come up with an example that actually gives you the worst case scenario, and then try it out, and then say, yeah, I'm good. It's not going to overwrite. Okay. In this example, it's a little weird. So I don't think I can't think of twisting this a little to make it fail at this point. So we'll come back to that if we need to. But it's pretty straightforward as to how to do that. Now, if I so translating this to code should be what? How many lines of code is this? 5, 6 lines of code, because you're trying to figure out. If you just figure out which one needs to go, you go and you move the corresponding pointer up.
Right, that part is easy.
Now comes the next one that you said, which was, when do you stop?
Right.
We can stop when we run out of B, because we are merging B to A.
What happens when you run out of A first?
We won't, because
You could run out of A first. You haven't run out of B. What happens if you run out of A first?
if we, I see. Okay.
Any of it we can run out.
So everything in the B we can put down.
As soon as we run out, we move out of the loop and then.
The simplest case, the simplest code you can write is when you run out of either array, you just take all the rest from the other one, using a second loop. And it actually, and something the book does, which I didn't think about, is that because you're merging the same array, there might be a case where you're moving from the same place to the same place. So you can just skip the whole thing.
That will only happen when you run out of.
Yes, right.
Once you run out of B, you're actually moving from the same place to same.
Yeah, that's a kind of interesting case that I think is there.
If you run out of B, you're done, because everything in A remains wherever it is. If you run out of A,
We have to copy over.
then you have to copy over everything that is left of B into the gap that is still left. And what happens if you don't have enough space to copy all the elements of B?
That will not.
That means the problem statement is clear, right? That won't happen, because you would have, with that mode, you would have vacated as many elements that are left in B right there. So we are good with that. So this should be a very simple coding exercise, 6, 7 lines of code.
There's a harder way to do it too, which is the way I attempted the first time I solved this question, was to use one single loop and make the condition complex. Like once you passed 0 and went to -1, then you just keep taking from A using the same loop at that point, without having to have multiple loops. But it gets a little bit tricky to figure out where your stop condition is.
So generally for this, right, keep it
Simple.
simple, keep it straight, one for condition. So saying I'm comparing between the last element of B and the last element of A, and I'm trying to pump it into this element. That's all I'm trying to do. So if A is greater than B, then put A, and then do the variable increments the right way. If B is greater than A, then do that. What if they're equal?
Either.
Take B. If they're equal, take B.
You need to ask the
Take B.
question first.
No, what
It will be taken care by the else condition.
Okay. All the elements here are less than 45, all the elements are less than 45. Now what do I do? Which one do I pick?
We
So I
should
said
pick-
if this were to be 46, right? I said we'll pick this. If this were to be 49, we said we'll pick this. That's what we said. Now they both are 45. Now what?
We should always pick from B, because we have to merge from B.
No, we can pick either.
It doesn't matter.
Either you can pick either.
If we pick either anyway, we are moving that element, and then we are gonna merge B at the end.
So I heard 3 answers. Okay? I heard pick from A. I heard pick from B. And I heard pick both. So far I have not heard pick neither. Okay? So very clear. Right? Pick neither is one that won't work. Pick from A will work, pick from B will work, pick from both will work.
Yeah.
Okay? Why would you choose one versus the other?
So I'll choose B because suppose I pick from A. At the end, I have to move all the elements from B to A anyway.
But anyway, you have to move the element from A.
We can pick either.
So say it will be more optimized if I pick from B, because then I don't need to tweak that element remaining in the B later. Suppose all are same element A and B. If I always pick from A, then at the end I have to move all element of A to the end, and then
in the worst
copy
case
the B.
scenario, let's assume that you have 10 elements of A, everything is 45. If 10 elements of B, everything is 45, right? That's what you have. Now, if you always pick from B, you would take all the 10 elements of B, copy it here, you're done.
Yeah.
But otherwise, what you'll do is that you'll move all the 45 of A to the right, and then you still have to copy the B anyways,
Okay.
right? Since the B has to be copied in, so that's like definitely a score 1. Prefer A to prefer B. I think prefer B is actually preferred, clearly. Okay. Now the question was, why not prefer both?
There's no need to have one.
Go ahead.
I would say we can do both at the time to avoid just one extra loop. Like when we get 45 at both A and B, we can directly like copy both of those and increment the pointer so that we can avoid one extra.
So at this point of time, we're not talking about specifically about big O, because we are talking about, I mean, at the end of the day, big O is for worst case, and we are trying to, you need to find ways to make it go. But we are trying to optimize on the fringes, right? So if there are 10 elements of A, all 45, 10 elements of B, all 45, if I keep picking from both, then what am I doing? I'm still moving the elements. I moved this A in the B in the end, and then I also moved this. I moved the second one, I moved this. So I'm actually moving all the elements, which I don't have to if I just pick B. So the challenge here is that I would prefer pick B, because it's just easier, keeps the code clean. Like if A is greater, only then move A, otherwise you can just pick B and call it a day, and that just works. Because if there's only 145, like in each of them, then I will pick B first, the next number is going to be less than 45, and I'll pick A next in the second loop anyways.
Yeah.
So
Then you have
doesn't
another test case to add for this special case.
yeah, you don't have to add a
If you're
special
going to move
case,
them
like,
both
yeah.
at one time.
My code complexity
Yeah.
actually reduces. The right, like when I'm writing whiteboard code, I would prefer writing as little lines of code as I can. The fewer, the better, right? So I would prefer not to write the both for that reason. A is like prefer A versus prefer B. I think prefer A is a bad idea, because the example we just said, you'll end up moving all the elements. So always try to get to the ridiculous cases where like all numbers are the same. Now what, right? It's much easier to handle. All right, so that takes care of this question. Now what would you do if I told you that the question was not this, but the question actually was, you have A and then you have B, okay? I want you to rearrange it in such a way that all the numbers of A, then followed by B, essentially the sorted array. So which means that this number is less than this number, or like, if I concatenate B here, right, then the full array is sorted. So if I have, for whatever it's worth, if I had 1, 3, 5, 7, 9 here, and 2, 4, 6, 8, and 10 here, I want the final output to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Combined sorted array, no extra space. A slight variation to the problem, but actually makes it super complex. So now this is the problem solving question.
You have to swap here.
Yeah, you have to exchange. So you have to use, and you don't have extra space in the sense that you have constant space. So you can use like a few variables here and there if you want, but you can't say I'm going to create a third temporary buffer where I'll put everything and then I'll break it back. Right? That's not a thing.
Move the even number from first array to odd number question.
No. First question is, we talked about the problem. Are we clear about what the problem is? Do you know what it is? Good. What does it resemble? Any problem that you've seen before?
The one we saw previously.
But all the problems that you've done before there's always extra space available. So have you ever seen a scenario where you need to merge two arrays or to merge two somethings without extra space?
Quicksort kind of resembles that.
So one of that's clever. Because one of the things you can do is assume, like, I don't care if this is sorted or not. I don't care if this is sorted or not, right? I can actually write a quick sort function that can actually work on two different arrays which are just concatenated, and I can just quick sort this independent, right? I can do that, and that will work. So that's a clever adaptation of something that you know otherwise, but then you're not making use of the fact that these arrays are sorted to begin with. So this is an answer, but it's not as efficient, which is still okay. I mean, you could actually do like a bubble sort, right? I can go take the largest number from this entire thing, move it to the last. Then I can find the second largest number of the entire thing and then move it to the second element. I can keep doing that. That's bubble sort. Right? I can sort these two things assuming that they are just concatenations. I can do that. That'll get the job done. But that may not be the most efficient way of doing it. But that's actually pretty clever. Looking at this as a quick sort. Like I know how quick sort works. I know that my goal is to get a final concatenated eventual sort. So if this were to be an interview and you come up with a quick sort algorithm, I would run with it and I would say, let's go do that. I know it's not the most efficient. I know it's not the most effective. But this is not a plain vanilla quick sort. This is a quick sort which actually is using two different arrays. So there are too many edge cases for you to figure out and make through. Algo, I like it. You understand how the algos work. Data structures, I actually love that because you are able to manage two arrays as a concatenated array. There's a lot of boundary conditions around it. That's also great. So I love this. So this would be a question that I can use to evaluate your problem solving, algorithms, and coding. And I would just go with it. So as an interviewer, if I pose this question, as a candidate, if you come up with hey, I think I can use a quick sort, even if that's not the most efficient way of doing it, I'm just going to go with it and say, let's solve it. And if we solve it in reasonable amount of time, you already made it, in my opinion. And then I would probably poke at you to see, can you do better than that by saying, hey, but you're not using the fact, now what, right? And then we can try to come up with a better algorithm, but I will not force you to code that because we will not have time, for sure. Anyway, so that's a pretty clever way of doing it. Go ahead, what else?
So, I mean, what difference does it make? Even though we don't have extra space, we can do the same algorithm which we did previously with a little variation. Like just the two-pointer approach again, both are, it's given that it's sorted. So now I will only fill up from the first position of the first array. So if the first...
So you're filling up from the first position of the first array?
Right.
Okay, so what am I putting? So what am I putting here?
So I'm comparing 1 and 2 basically.
So the only candidate for this slot is either of these two.
Right.
Okay?
Right.
So what do I do next?
So I realize that 1 is less than 2, so I move on to 3.
So
I leave 1 there.
So this is done.
Yeah.
Now this is a candidate.
Yeah.
And this is still a candidate.
Right. So now
Now what?
I swap 2 and 3 because 2 belongs there. And my other pointer, I will keep it on 3. No.
I just did it. I changed my original question. Now go on.
Okay, so 1 and then now you're comparing 2 and 4. So, I see.
It will break.
So I know how you're thinking. So that's why I switched it around so that so if you did this, right?
Yeah.
2 is in the right place, but 4 is in the wrong place.
Right.
And that messes it up.
Yeah.
But then we are saying that array is sorted, right? So 3 should
Heap
come.
makes it. Heap makes it. What does heap make this? Extra space.
Yeah.
You don't have extra
Here
space.
is,
What's this? How much space can you're given constant space?
So again, you do the heap of 2.
That's just two variables, two numbers. You can keep that, but the heap will not help you because you will run into the same issue. So this should be the in-place merge sort question. Like how do you actually, so in a merge sort, if you look at the definition of merge sort, it's like there exists some in-place algorithm for merge, which is beyond the scope of this discussion, is what it actually says every time. You see that? It's like for all practical purposes, the interview question is merge sort. Let's assume that you have extra space to that's twice the array, so that you can actually merge with offer and buffer, and you can deal with that. It's almost always how they say. The classic thing, the only thing that you want to do is, what was your goal by doing this? Right? You did the 2, so you got the 2 in place. That's good. What was your goal?
Now I have to insert 4 in the right place in the bottom array.
Your goal here, this is a sorted list.
Right.
So with the log n approach, I should be able to figure out where do I insert the 4. I know I need to insert the 4 here. And how do I insert the 4 here?
Bring everything.
By actually shifting. If stuff happens and the thing I have to insert is somewhere in the later element. So my goal is once I'm done with it, I need to have a clean array where this array continues to be sorted, this array continues to be sorted. All the elements which are here are less than the element that is here, the first element that is here. That's what that's the goal, right? That's what. And once I'm done with everything, I'll have this. In order for me to do that, what I need to do is this swap is okay, this push to that is okay, but when I swap back, I need to actually find the right location to insert it and then essentially shift everything one by one. Can I do better than shifting things one by one?
Shifting is taking a long time.
It will, but can I do better than that?
Without space?
Yeah, with no extra space. There's no good way. There's no way to do it. That is it. And that algorithm, the worst case of that is essentially m times n, essentially, or n square, depending on what it is. If for whatever reason, right, if every element of this was greater than every element of this, like if you start with this array on the top and this array in the bottom, right, then you, for every element you have to keep shifting, right? And that's an n square algorithm, and there's nothing much you can do. But you can't do better than that.
So can I just sort the first one without worrying about the second one, and then do a sort on the second one later on?
How do you do that? What do you mean that?
Like,
They already sorted.
just keep swapping and making the first array in order, and don't worry about whether the second array is sorted or not.
It's not just a question of sorting. You need to keep track of the minimum element on the second array, because I want to make sure if this array is not sorted at every step, then this element is not the smallest element, and this is not what you have to compare. So in the other example that I had, where I had essentially I flipped it over such a way I had 4 here and I had 3 here. If you end up comparing with 4 all the time, right? Let's assume that this was 40, not 4. Okay? I will not swap this out. 3 is the next element that needs to go here. You would not even know that. So that's the challenge, right? So essentially, what you're looking for is you're looking for the magic pivot that actually gets you half the elements in the left and half the elements in the right. And so one of the other ways to solve this problem would essentially be to find the pivot. Like I can find the given two. This is the median of medians, right? So how do you find the median of this array? How do you find the median of a array, which is like one array which is sorted, the middle element? How do you find the median of a bunch of arrays which are all independently sorted?
You could either merge them and then find out.
No merge yet, right? You don't have to merge them. So the median candidate essentially is this is a median candidate for me. This is a median candidate for me, right?
Yeah.
Now you look at, so essentially what you need to do is you need to go left or go right in both of them in such a way that you can actually identify that point where numbers less than me is k and numbers greater than me is k, and that you can do that in essentially log n time, because it's kind of like a binary search modified. So once you identify the median pivot, what you can do is you can identify all the elements that are greater than median here and all the elements that are less than the median here, and then execute the swap, which is not sorted. Then you can run the sort. So there are different algorithms that potentially will work, okay? And none of these algorithms are actually standard. They are not, and at this point of time, if for some of you, if this is not something that you're following, this is more advanced than what we normally would be expecting in interviews, and this will probably be this is where you're looking at. I'm looking at folks to be super proficient at this point of time. So take these concepts down. Anyone who actually wants to code either like a quick sort, which is actually on 2 different arrays, try that. That's actually fun to do, where you don't care about the pivot as such. You're just looking at a random pivot and finding a way to sort it, like sift it. And then the second approach is to use find the median and then do a swap and then do a sort. Or the third thing is your approach, which is actually to swap but then find the right spot to insert it. So in all of these cases, right, the data structure that is given to you is already like your hands are like shackled. You don't have a good data structure to help you with this, so you'll have to come up with some stupid algorithm to compensate for the gaps that you have in the data structure.
So that swapping thing would be the worst case one?
Swapping thing in the worst case could be n square. It will be n square.
So is that solution actually the what do you call the in-place merge sort? Is that swapping thing actually the real
You can use
number?
any of these techniques for that,
But then it would become n square, right? The merge sort if we use it.
which is so I don't think there's a O of n algorithm for in-place merging of 2 arrays. The best you can do is the n log n, which is essentially the median algorithm that we talked about.
So n log n in place, you're saying that is what we can use.
Correct. It's twice of n log n, because you have to do first you have to sort it, and then you have to find the median, and then you have to swap, which will again break the sorting, and then you have to resort it.
Okay, and one more thing, how can we call it in place merge sort? We already, the stack is taking up space, right?
Where is the stack here?
So, in merge sort I'm talking about. So, we are breaking up the array and reaching, a point where we start merging one element individually. So it's already, the stack space is occupied. So how can we call it in place, even though we are just saving this, the subroutine space?
We are only merging in place, right? We are not sorting, it is
No,
already
no,
sorted.
no, merge sort.
Let me rephrase the question. Let me rephrase the question.
Or iterative.
So, not this question, but typical merge sort, if you have 1,000 elements, you break it into two 500 element chunks, right?
Yeah.
You sort the left half, you sort the right half, and then you merge them both. That's what you're doing. How do you sort the left half? You break it into two 250 element chunks. How do you sort that? You break it into 125 element chunks. Now, as you're going through this process, you will be going through, you're recursively calling sort left and sort right? So as you're calling recursively sort left, you're going down all the way up to when you have one element left. So this operation, what is the depth of the stack?
Log n.
It is log n. So it is in place merge sort, but it's not O of 1. The merging operation is happening in place, but you will need an auxiliary space of log n to keep track of the stack. So just playing with the nuance here. Typically when you say in place, you're expecting no extra memory. But here you do use extra memory. The log, you have to use log n. If you had, instead of it being 1,000, it had been like 1 billion elements, it's not constant space, right? It is still using log n space. So,
but here we are performing only one step operation of merge sort, right?
correct. It's a very small portion of the merge sort.
But I'm not able to understand why do we need stack memory here?
There's no stack memory for this one, which is why the confusion was, because this question does not require a stack. The stack is required for a merge sort, not for this one.
Okay.
Even the merge sort we can do without stack, right? Like in the loop, like using while loop.
So, the things like he mentioned is like when you do a merge sort, you divide the strong a lot. So it means the stack in the memory, the physical memory is built up. It's not mean that he used a stack data structure in here.
I think we don't know the in-place merge sort algorithm, so we don't know that use recursion.
Whichever algorithm, whether it's in-place merge sort or like
So we
generic
don't know
merge
whether
sort.
that use recursion or not. Is there a
Fine. If any algorithm that is actually doing dividing and conquering, you are dividing it into two groups, and then you're dividing each into that into two groups. So at all points of time, you will need log n depth because you have to keep track of all of those groups, right? A million has to become 500,000, has to become 250,000, and so on, finally till 1. So you will have a log of 1,000,000 in that thing, anyways. Right? The number of steps you need is actually less. Right?
But now recursion, it'll be smaller probably because the stack space is bigger in general. than
Sure,
point.
sure. All right. So that takes care of that. Okay. So now let's do. So this is like next question. So I'm not going to focus on coding at all. So please code. Write the code down. If you've already written the code for the first one, great. Please write code. Pick one or more of the options that we just discussed. Try to write code for that. Okay. The next question was actually super trivial, which was essentially sort. Essentially, you wanted to given a sorted array. I want you to search for an element in a sorted array, but you're not given the size of the array. Right? If imagine it was some sort of like a linked list, but you had the ability to jump as far ahead as you can. It's some kind of a linked list where you could put, you can jump ahead, but you will not be able to. You'll not be able to, like you can go back, but you can't go. You don't know the end of the thing. Another example of the same thing was essentially a very trivial scenario was that if I give you an infinite sorted binary stream, identify the point of inflection. What does that mean? It's just a fancy way of actually saying the question, but what does it mean?
Can you repeat the question?
Given an infinite sorted binary stream, identify the point of inflection. What is the point of inflection? So okay, first, what is a binary stream? Contains zeros and ones. What is a sorted binary stream? Contains all zeros on the left, all ones on the right. That's what it means, right? So it's an infinite sorted binary stream, right? What is the point of inflection? Where it actually goes from 0 to 1. The point where it actually is 0, the next point is 1. That is the point of inflection. That's it. It's just a, like, as long as you break it down, it's pretty straightforward. How do you find out? How do you, given an infinite sorted binary stream, how do you find a point of inflection?
Expanding a scope.
And all you can do is you can actually ask for, get me the next k bits. You can always do that. You can say, get me the next 5 bits, get me the next 1,000 bits, get me the next million bits. You can do all of that. The goal is to actually find out where it stops. Like, you can't say get me all the bits because all the bits don't exist.
So you have to find the index of inflection?
Yeah, at the where does it switch from? So a bunch of zeros followed by a bunch of ones. Tell me what location is the last zero. Tell me what location is the first one. It should be like right adjacent to each other, right?
So if we are splitting them, then we should also track where we are splitting and how many are we taking, right? If I take next k elements,
So one of the ways that people have done is like, you know what, I'm just going to take 1,000 blocks at a time. So I'll take 1,000 bits, and I read the last bit of the 1,000. Is it still 0? Like, yeah, it's 0. So get me the next 1,000. Still 0? Get me the next 1,000. I can keep going. The moment I see a block with 1, that means that 1,000 began with a 0. Like, at least I know that the previous block ended with a 0. I know that. Only then I went to this one. And I know that this block ended with a 1. So the point of inflection, the first one has to be somewhere in this array. That's all I know, right? You could do that. But what's the complexity of this operation?
If the last element is the only one that's 1.
Log n.
How's it log?
Order of n.
It's order of n, log n. So let me repeat my algorithm. So let's see if we can actually get to the bigger property, right? So all I'm trying to do is, the goal is to find the first one. The first one that you see in the stream, the index of the first one is all you need to find out. So what I'm going to do is I'm going to ask for 1,000 elements. I compare if the last element of the buffer is 1 or 0. If it's 0, I just discard it, I ask for the next buffer. I keep asking 1,000 elements at a time. If I see a 1, then I find the first one in this block. That I can do using binary search, right? I can figure out binary search for this block of 1,000. So, in order for me to do that, what is the time complexity of this operation? Log n? How is it binary search? It's only log of 1,000, right? The last is the only place I'm doing binary search.
Constant.
I'm only getting 1,000 elements at a time. So if the point of inflection, okay, how do you define big O here? So if the point of inflection, this is the reality, and this is the number of operations I'm doing. If the point of inflection was, like, say, the first element itself, right? Then how many operations will I do? I'll get the first block. Okay, then I will do binary search. I'll do log 1,000 because in order for me to get to the first element, it's a log n operation, right? So this is actually one operation plus this log of 1k, right? If this was like 1 million was the location, how many operations do you have? How many blocks do you have to get?
1 million by 1,000.
1 million by 1,000, and then plus log 1k, right? I need to do. So then if it's like what it's n, then what is this? That's it, right?
N is n.
So which is what? It's n by 1,000, which is n, right? So this is log n. Can I do better than that?
Can we get only 1,000 or we have something else also
You
available?
get as many as you want.
So can we get
everything.
a specific number?
Huh?
Saying that give me the 1 millionth number or give me the 1,000, I mean only that one number, one bit.
So it's a stream, so you can't.
Okay,
But
but
expectation is that you can say, get me the next million bits. It will be given to you.
Can I do
Okay.
bit
So assume that there is no limitation in terms of data structure, size, storage, array, nothing else. You can just do that. There's no limitation. What you said, but let's folks get to it. Go on.
Yeah. I mean, it's a binary search problem where we don't know the end, so we start with 1 and keep multiplying that.
And that's exactly what this problem is also. It's essentially an expanding scope binary search. So binary search, we've done this before as well. There's a good if your intuitions are in the right place, sorted array, sorted stream, it's good. So essentially what you do is you start with 1 at a time. 1, 2, 4, 8, 16. You just keep doubling your scope of search. And as long as you're still, is the 16th bit 1? Like, no. Okay, then is the 32nd bit 1? Like, no. Then 64, then whatever, 1 million. You keep doubling, keep going, right? At some point, the 1 billionth bit will be 1. Now what do you do?
go down.
In the last section, we'll do normal binary.
Yeah.
Or
Whatever that range is. we'll go
I,
down.
every time I hear that answer, I like it, but I'll tell you what. So then, now we know the size, right? Now we know, whatever this is, I know, so essentially I know that this is a 0, I know this is double, this is 4 times, this is 8 times, right? And this is 16 times, or whatever that number is. And I know that this one is a 1, so that 1 is somewhere here, right? So in this section, I know there's a 1, and I know this was a 0, only then I doubled it. So I could do a proper binary search because now I have a bound, right? I don't like this answer.
Can
Why?
we do the same thing again, starting from there?
So why I don't like this answer? It's not a wrong answer. It is the right answer. It works. It actually doesn't have anything in the complexity, nothing outside. But the thing is that you're being introduced to a concept of how to do expanding scope binary search, right? So what you should do, what I would have preferred you to do, is that I would reset my scope. Start with this, then double it, then quadruple it, then this, right? If I did that, then I will find that that thing exists somewhere here, so I don't have to even go here. Then again go to 1. Keep repeating it. So essentially what you can do is you can do the same expanding scope binary search over and over and over again, and you will still get to the same value. Okay? Nothing wrong with it?
No, yeah, but still I can say, since normal binary search, in case some utility method is there, I can use, this is something new, anyhow this logic I have written already, right?
You already written logic, so you can just reuse the logic, and that's it. So you're not even relying on existence of like a binary search at all. I mean, why would I write an expanding scope? So if to solve this problem, you are now writing an expanding scope binary search, and then you're writing a binary search for the other one, which doesn't make sense, right?
So how does the order change between doing a straight binary search and expanding on that limited set?
That's n log n anyways.
Okay.
It's the same thing, n log n, right? And you're doing the same thing. This operation is also n log n, and the fact that you're doing a binary search doesn't change the complexity at all, right?
Log n, right? Not n log.
Oh, sorry, log n,
Log n.
not n log n. It is log n.
Log n.
Thank you. It is a binary search, right? So you're not sorting, so it is binary search. So to identify the point, you're just jumping as much as you can, so it's log n. Thank you. So it doesn't matter which one you pick. I don't think there's anything wrong with it. But as an interviewer, I start looking at this, and the one question I have is, why would you want to write more code?
Yeah, okay, that's what I was thinking. Yeah.
Right?
Reuse your existing.
Yeah, just
Yeah.
reuse and you're good to go, right?
Right.
You can definitely do that. And that's all this question. This question is all about this expanding scope binary search. And we have applied this problem in so many different forms. So one of the advantages that this offers is that the expanding scope binary search actually, when would you use expanding scope binary search even if the bounds are known?
If it's too long an array or something.
Even then, it's the same the approach. So one of the questions, we've done this like many months ago. So for folks who don't remember, even if you're here, I wouldn't be surprised. The question is essentially find the highest bit set in a binary number, right? You can't binary search it. It's not sorted. But what you can do is you can actually create a bit mask, which is essentially 1 0 0 0 0 0 0 0, and then add it to see is it like still non-zero. Then if it's 0, then you still haven't hit it. Then it's double. Then it's 4. Then it's 8. Then it's 16, and so on. So your bit mask, the way you construct your bit mask, is actually expanding scope. And when you AND it with your number that you're looking at, you will get the hit, which tells me that none of these bits were ones in the number, in the original number, and the 1 was somewhere in this block. And the moment you get this, what do you do next? Reset and continue with 1 bit and then 2, right? That's why you need to reset the bit mask from that point. So you're just changing the scope. Same concept. So now you need to add this expanding scope binary search to your tool belt and make sure that you know how to use it and write code, write it a bunch of times for different things, and then you will see that you can actually apply it to a problem which is not actually a binary search problem. Technically not a binary search problem. Okay, it's not sorted, there's nothing there. Okay? So, any challenges with this so far? Any questions, any concerns? Say again?
You know the length of the bit set.
Yes.
Then why don't we start from the midpoint and do like.
But it's not, your goal is to actually, the bits are not sorted. Your goal is to find the highest bit that is set.
Okay.
The bits are not sorted. So now what do you do?
Oh, I see.
So you could do the same masking approach there as well. So what you could do is you could create a bit mask, which is 1 1 1 1 1 1 1 0 0 0 0 0, and you could try it out. If this results in 0, that means your answer is not in the left half, the answer is only in the right half. If this result is not 0, then the answer is in the left half and not in the right half. Then what you can do is, again you can do 1 1 1 1 0 0 0 0. So you are doing a binary search here as well. This is the expanding scope one, this is the regular binary search. So you could do that. So again, another example of where it's actually used is that. It's far easier to construct this bit mask. Actually, it's just math. You can construct it both ways. So that's the other way of, that's the other part of the equation. Does that make sense? Why? All right. So that takes care of the second question, or the fourth question in the book. So this question is actually the book covers it in a subtly different way. So what they're doing is they are potentially using a way of actually just jumping twice every time, and then identifying the end of the array somehow as the first pass of sorts, and then using it to figure out. Right, if you find a value that's greater than where it is, then you've already limited your scope. Then you can do regular binary search after that. Not happy with that approach as such. I would prefer to add this to your toolbit of how to do expanding scope or binary search. All right. Next question is this one is the one with you've got like a whole bunch of numbers, and some of the numbers are missing. Find a number that's actually missing. So the given example is you've got like 64-bit, 32-bit numbers, 4 billion of them. There are about 4 billion numbers in total. I think 32-bit integers. So of the 4 billion, like 4 point some billion, you've got 4 billion already there. So 93% of the numbers are already in. So your goal is to find a number in the other 7% that is not there in the list. Like a way of how do you generate a unique identifier for something? Like, I'm trying to create customer IDs, and what I wanted to do was I wanted to create random customer IDs just to kind of throw people off. So my algorithm was create a random customer ID. If it already exists, then create another one. If it already exists, create another one, and I went on doing it. I've been doing it for the last 5-6 years. Now, unfortunately, I'm so much at the end of the space that I'm getting a lot of collisions. So in order to create a customer ID, I'm spending like hours before I get to the customer ID. So now what I want to do is I want to go figure out like what is the lowest number that is available for me to use. So now I've taken a problem which is just there and translated it into like a meaningful real world problem of sorts. I don't know why this is a real world problem. I really don't want to work for a company that actually did this as a strategy. So, but I mean, you don't choose them. So, all right. So this is what we had. Now, what do you do? How do you figure out? What's your approach? What's the objective? What type of question is this?
Somehow we have to remember.
No. Oh, okay.
Problem solving.
Problem solving.
Problem.
Why problem solving? I don't disagree. Why problem solving? Why do you think it's problem solving?
How do we find the ways?
So you're given like a construct, you're given a setup, and the goal is to actually find the outcome, right? So it makes sense. And you need to come up with a creative way of doing it. Use auxiliary data structures as necessary. I think the book says you've got like a gig of memory available, or like 10 megabytes of memory available, and so on. So how do you actually solve for this problem? And if you have minimum memory available, something like that. Okay. So walk through this.
You're supposed to be finding out the numbers which are available to be used.
Correct. I want you to tell me the lowest number that is available.
Okay. And so you've been assigning numbers also while.
I have been assigning random numbers. 32-bit integers have been assigned. 93% of the numbers are consumed now. Only 7% left.
Okay.
Random distribution.
If you have a means of finding out whether it is already used,
Yeah,
then
that's all I have.
Yeah, then you can use the same concept which we used earlier, like pick one, then pick two.
No, it's not.
It's not
Or you
solved.
might skip the. if these are all integers, so if you're saying that there might be around 4 billion of them, or covering almost everything, so you're maintaining a sorted list of integers, right? So you can compare it with the index.
Not sorted yet.
It's not a sort.
It's not sorted, but there's an implicit sorting available, but go on.
Okay, then if you can compare it with the index. So if my 1 has to
So
be in
if
position,
my array of numbers is sorted, right? How do you figure out what's missing? What's the lowest number that's missing? That's a completely different question from what is asked.
Where the index mismatch.
Yeah, but
So your the number in the ith index has to be I.
Yeah.
Okay, can it ever be greater than I?
no, it can, but that means
How?
No.
It
cannot.
can be.
it
Cannot.
Yeah.
It can be less, but not greater.
It can never be greater because these are unique numbers, right? At the very minimum it's equal. If it's equal, what does it mean?
We have to go further.
If it's equal, all the
All the
numbers
numbers
lower than me are actually at the right spots. Correct?
Yeah.
That's what it means. If it's less than the number, the index, if the 1000th element is actually like 800, it can't be 800, it'll be more than me, right? So it'll be like 1005. What does it mean?
So
Not just something. I know exactly how many numbers are missing.
5
yeah.
I know that 5 numbers are missing. Only then 1005 will actually be in the 1000th index, right? So I got that. Now now what do? I know that there's a number less than 1000 somewhere in the between 1 and 1000. I know at least one number is missing. What's my next step?
So we half. I mean, so same thing.
No, it's reducing. It's normal. There's no expanding scope. Sure. So in this case, since you know that it's 4 billion, so you know the end scope. So technically, you can just go to the middle and keep jumping. But then the thing is that if the numbers are properly distributed, evenly distributed, then it doesn't make sense. You know, you can start expanding scope. That's much easier. That's one thing. But let's go back to this question. So essentially, all you can do is you can just binary search this. If you have the numbers in sequential order, you know the index. If the value is actually the value at that location is greater than the index, then you know that the problem is in the left half. If the value is equal, then you know the problem is in the right half. And that's it. You can just keep going. And your goal is to find the smallest number that is missing, and you can just use that to go for it. This is if it's sorted. What if it's not sorted? So now this is why it's a problem solving question, because depending upon what the construct is, your algorithm depends on which you pick the right set of algorithms.
So I think that you can create another array would have the same size with that array that you had before, with the original array, and whenever you read the index, you justify. Whenever you read a number, you justify the index of the second array and put 1 or 2, like another like 1 or 0 in there. And whenever you fill, like you just like after you fill up this one using binary chart to find which one is the 0, the first 0, and you're done with it.
Okay. So how is that different from me just saying is 1 in the list, is 2 in the list, is 3 in the list, is 4 in the list, and just got the answer?
Can we try to solve this for 10
How is that any
numbers?
different from what you just did? O of n. You just went through the entire thing. And you are setting zeros and ones. I don't know why you have to even set zeros and ones. The moment it's a 0, you stop, right?
No. I will throw up things, but like in each number, because each number you can use that each number like an index of the second array. So you can mark this index into 1, and after you read the whole array, you can check the second one, like which one is the first 0 in that array. You create the first 0 array. That's what I did.
So because it's not sorted, this is one way of probably just putting everything in
Yeah,
there. Sorting
you
it.
put everything like based on the index, based on number of
If
arrays.
I were to play it back, what you're looking for is essentially use a bit vector,
Yeah, yeah.
and you're trying to set the bit vector to 1 or 0, depending on it. Set it all to 0. Then for every number you found in the second array, you're just setting the bit appropriately, right? So that and then you're trying to find the first 0 bit that is set, so that you can identify what it is. There is no good way to find the first 0 bit set. So you have to go through sequentially.
You can use this binary search to find the 0 bit set, right?
How do you use binary search to find the first bit set? There could be multiple of them, so how do you know that?
No, I think he's talking about the same approach which we talked
Yeah,
earlier.
so like you have the 0 first, and you fill out the 1 later, and when you fill out the whole array, use the binary search to find like where is the 0. You always find the left half because like you want to find the left half first, and after that you find the right.
How do you do that? Walk me through again. Because what I'm missing here is that what you got.
Yeah.
Right. Let's assume that it's like let's stop the billions and make it just small numbers. All you have is this is 0, 1, 2, 3, 4, 5, 6. That's all you have, right?
Yeah.
Okay. Now this is 1, 1, 0, 1, 0, 1, 1. Only 2 and 4 are missing between all the numbers. Now if I don't know how do you do binary search. If I do binary search, I'm actually cutting it into half. There's 7 elements, so I cut it into half.
Yeah.
Now how do I know that there is a 0 to my left or 0 to the right? How do I know? This element is a 1. Now what does that tell me?
So like you run the left first, and if in the left they have a 0, so you can cut it one into the half.
But if you're processing both the halves, then it's not binary search. Right?
Yeah.
So I'm just trying to make sure. Like if you divide something into 2 parts and then process both the parts, then that is not binary search. That doesn't give you any advantage. You need to eliminate one versus the other right off the bat, right here.
Yeah.
Like in a binary search, what we do? We look at the number and we say, oh, the left half is smaller than the right half, so this number, so the answer is not in this half, it's only here. So we completely kill half the elements in one shot. Only then binary search works. So this won't work for you. So in this particular case, what you've done is you've gone through the entire array, and then you've created a bit set. Now you can go through the bit set, and you can figure out the first one. But if you were doing this, then you could do the opposite also, which is essentially say, check if number 1 is there in the list, number 2 is there in the list, number 3 is there in the list, number 4 is there in the list. Because that's exactly what you're doing here.
Yeah.
This is just helping you figure out if number 1 is there in the list or not. Right? What we said was we have a function already available that does that, right? Get if 1 is in the list already exists for you. So that's, you're creating a bit set to help you with that. You don't need a bit set for that because that function already exists. Okay, so you could go through this.
We start from the left and have an expanding scope like bit mask and then see audit and see.
Well, the bit vector, fair point. You could do that if this was like a real binary number which you can potentially use the same thing. So then you can do the binary search, totally. So the book actually is not, the way it's actually explaining the question is that it expects you to, the array is just given to you, and it expects you to construct the bit set yourself. And then once you construct the bit set, you can go through the bit set sequentially and find the value. And the expectation here is that you are only, you will find something in this bit set, and the expectation is that then the numbers in the array is already large enough. So it's not like you only have like a very handful of numbers or something in that thing. So as you go through that, you can find out what the answer is. So that works. So let's do the book question. Okay. So given an array of numbers, and let's assume that you don't have enough memory to create a bit set. Right? You don't have enough memory to create a bit set for like 4 billion numbers, and 4 billion bits is essentially even at 8 bits a byte. That's a lot. So what do? 4 billion is 4 gigabytes.
Brute force in place like merge sort or something, and then
They're not immutable. The data is immutable, so not mutable. So you can't change the location. You could do essentially n square search. You could, right? And I said you don't have enough memory. The question probably would be how much memory do I have? Would be probably the first question I'd ask, right? So one of the strategies that I've seen effective here is that if I know, since I know it's 4 billion numbers, let's assume that I have the capacity to store 10 numbers. That's it. I can only store 10 numbers. How do you solve it?
Pick 10 at a time.
What do you mean pick 10 at a time?
So you're looking for the first 0, right? So, or in our case, we have a function which tells us. So
There's no function. We're doing the book question. So the book question is that you give an array of billion numbers. That's what you have, and I'm telling you that you only have space to store 10 32-bit integers. That's all you have space for. Okay. How do you find out the smallest missing number? Of all the numbers that are missing, how do you find out the smallest one? Say again? No, what 10? What 10? Do what 10?
The first 10.
From the array. Well, how does that help? Like I take the first 10 number from the array, put it in this. What do I do after that?
Then you need to pick up the next number and try to knock off one and then put that number
But I don't know which is missing. I don't. This is the opposite question. Right? If the number is there, then I can do it. I can keep it as like a heap
So,
of.
what are we supposed to find? The smallest number in an unsorted array.
Correct.
Of 10. So, you use a heap of size 10. And
Fine. So you have a heap of size 10. What does heap tell you? What does heap do?
It gives you the minimum element immediately.
But it gives you the minimum element that's in the array. It doesn't give you the minimum array.
No. So then we load the next 10. And
Go to the entire array. What is left? You're left with the 10 smallest numbers in the array, which is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Done. Now what? None of them are missing. How does that help?
I think like he made a right point that you can use the heap in here, but like after you make the heap, you can bring the smallest number and you can make this smallest number -1 because like the next missing number could be in the left hand side of this smallest number.
You got 0, so there's nothing less than 0. It's non-negative numbers anyways, and you have to find the smallest number anyway. So you got 0. So if you did heap and I got 0 to 9 in the heap, what next?
No, so you take out the 9th number, which is the max, and then keep inserting one number at a time and build a heap again. So it's like it's a time.
How will you do that? How will you do the next number?
No, once we get the new number, we rebuild
That's
the
an n
heap.
square approach, right? I have to go through the whole thing again.
This is not a good approach.
Okay.
So that's because at the end
No,
we
what-
have a smallest number at the.
Let me see if I can actually.
Can it divide that number with, find the remainder?
No, the book has. I'm not sure if you guys have actually seen the book solution. The book actually talks about this. I've changed the construct of the question a little, but the book, the thing in the book solution still remains. So then, okay. So here's what it is, right? So let's assume that we are only talking we're not talking about 4 billion numbers. We're only talking about 3-digit numbers. Okay, that's all we're talking about. Right? So now what I'm doing is I'm actually trying to find out numbers that actually begin, which has the first digit of 0 counted, number of first digit 1 and first digit 9. How many numbers do you think exists in this range with first digit 0? No. First digit 0. 0 to 99, which is what? 100 elements. How many elements that exist with the first digit 1?
Same.
Right? At some point of time, this will be like 86. What does that mean? Or what does that mean?
Missing in that range.
Missing is somewhere here. Nothing is missing from 0 to 99 because I found 100 numbers. Something is missing from 0 to 1. Nothing is missing from 0 to 2 because it's 100. Nothing is missing from 0 to 9. Something is missing in 8 because it's 0 to 35 or whatever. That's all I know, right? I got this? Can we get that? How do you get this? How do you get this? Go through the entire, all the numbers, and then wherever divided by 100 is actually 0, add 1 to this, divided by 1, 100 is 1, add 1 to this, and so on. You're done. Right? Okay? Now what's the next step?
Divide by 10 and do the same thing.
But if I divide by 10, I'm going to get like 11, 20, 36, 49. What do I do?
So the same thing, like 0 to 9 for the second digit we do.
Yes, but that will give me 100, 100, 100, right? So what do I do with it?
No, one of them will not match, right? One of them will not match, right? So,
but we don't have
you got 86 for 1 when you were supposed to get 100, which means that there are the smallest available element is it starts with 1. I mean, it's between 100 and 200, right?
So if I say this is pass 1, in pass 2, I did this. Okay, I got 100, I got 100, I got 36, I got 100. Everything is like that, and I got 20 or something like that. I got this. Now what does it mean?
So it means it's between 120 and 130, right?
Why? No. No. It could be because all these things missing are actually corresponding to 8. Maybe this is between like 830 to 890 were missing.
So now our bucket. So previously our whole all number was 1000. Now it become 100.
Why is, how is it 100? I have the entire array available.
No, we are now considering only taking the one.
We are ignoring all the others, right?
Yeah, we are just taking from 100
This is the
to.
assumption that you didn't state.
Yeah.
He just stated that now. So all you're trying to do is, so in this case, what you're trying to do is that you're actually trying to only numbers that are from 100 to 199.
Yeah.
You bucketize the second number. In that case, the max you'll see is only 10, not 100.
Yes.
So when I wrote 100, you should have said like, no, why are the 100 numbers? It should only be 10. Since you didn't say that, I know that you're not thinking about that way.
I said 100 to 200.
Even then,
Yeah.
even if it's 100 to 200, there are not 100 numbers with second digit as 0, right?
But we have a limited size, so how do we?
The size is only
remember-
10.
Then we override that.
Yeah, you don't need this anymore, right? You've identified that the problem is with 1. So now you can,
No,
you can override this and you can just start filling this
But
out.
at 1 we have 86, but at 8 we have 35 numbers. So
You don't care.
We want to find
You
minimum.
don't find the minimum anyway. Okay? Once you've identified 1 with 86, you're good, right? There are 14 numbers that are missing, and one of the 14 is the smallest case, so none of this is relevant. So here it might be 2, and here it might be 1. I don't care because the answer has to be like it's 1, 0 something.
Right.
Then again I go and do the same thing. So I need to go from 100 to 109. I do a third round and I can go. So what I've done is I'm doing digit by digit. I'm trying to vacate that, right? So how many loops do I need for 4 billion? How many times do I, what's the depth if it's 4 billion numbers?
How many digits?
The log is? Log of 1 million?
No, what is the memory? What is the our size of this array?
10.
10.
If I have only 10 integer storage, if I have 4 billion numbers, what is how many loops do I need?
Log 4 billion of base 10. Because every time we are dividing by 10 and then just taking the one bucket.
So you're doing one digit at a time.
10.
Billion has got how many digits?
10.
10 digits, right? So it's 1E9, right?
Oh, yeah.
9 zeros.
10.
So you've got 10 digits. The first one is only 4, but you can't help it. So you know that the answer is between 0 to something, or 1 billion something, 2 billion something, 3 billion something, or 4 billion something. And that you'll know the first pass. Once you're done with that, then you're trying to, now you know whether it's between like whatever the billion was, you know the billion number first. Now you're talking about is it like 100 million, 200 million, 300 million, 400, that you know that number next. And then you know is it 10 million, 20 million, 30 million. So you know which part of it that is. So you keep refining your filtering thing every loop, and in 10 cycles you'll be done. Correct? Now what if I had just 2 integer storage space?
Then you'll probably go for a range 0 to 5 and 6 to 10 or something.
But how do we build the range? Like, how do we?
Can we do with the bit rather than the divide by 10? Yeah.
That's all you're doing, right? You're doing it by bits. You're trying to figure out what the first bit is. If the first bit is set, add it here. The first bit is not set, add it here, right? So that way I'm expecting to, if there is essentially, I expect 2 power 32 numbers. So I expect 2 power 31 here and I expect 2 power 31 here exactly. If something is missing, then it's in this half. So nothing is missing here, everything is here, then it's missing in this half. And then now I can actually just ignore the first bit, now go for the second bit. For all the numbers where the first bit is set, find out where the second bit is set or not. And then I will divide into 2. For all that where the second bit is not set, third bit is set or not. And how many loops will it take?
How many bits?
So 32 bit number. 32. So this will take me 32 loops. Right? What if I have 3 numbers? What if I have storage space for 3?
I still use bit size and use
Just ignore the third one.
I like my thinking. Essentially what you're trying to do is you're trying to divide your entire space, like your space of 4 billion. Now you're trying to divide it into 3, into range of like 3 to 4 billion by 3, 4 billion by 3 to 2/3 of 4 billion, and 2/3 of 4 billion to 4 billion, right? So divide into 3 buckets, that's what you're trying to do. That's all you're trying to do. So the fact that it's easier for us to comprehend if it's numbers by 10 buckets is essentially the first digit. It's like easy for us to cognitively understand. For binary, we are programmers, we understand that a little bit. But the crux of the matter is that you're actually just dividing into buckets. The first half of the bucket is essentially where the zero is, first bit is 0. The right half of the bucket is where the bit 0 is 1. So it should be straightforward. So in this case, that's all you're trying to do, right? 3, if it's 7, is it 14? If there's like 31 elements or 37 elements, it doesn't matter. You're just dividing this into that many buckets. From your 0 to whatever your minimum is to whatever your maximum is, divide that into that. And then you need to have 2 additional integers, which are essentially tracking the lower half of your scope to the upper half of your scope, right? The upper end of the scope. So this thing, you're trying to keep track of 100 to 199, right? So you need to have 2 numbers that actually keep track of that. And then you keep narrowing it down by a factor of whatever to get to the answer. Okay?
What is this division? The 3 division? Like when you're given 3.
When you have only 3 buckets, you divide it into 3 buckets. That's it, right? So you know that you have to go from 0 to 4 billion. Whatever that is. So which means that you will go to 0 to 1.33 billion, 1.33 billion to 2.66 billion, 2.66 billion to 4 billion, right?
But you're looking at the actual digits, right, when you're working on this?
No. I'm looking at is it in range 1, range 2 or range 3 and I'm going to add it. Bucket 1 will only contain if the number you asked for falls in first bucket, then I'll add 1 here, or I'll add 1 here and I'll add 1 here, that's it.
So how are we putting in the buckets?
If condition comparing.
If the number is between 0 to 1.33 billion, then I will put it in first bucket. If it's between 1.33 billion plus 1 to 2.66 billion, I'll put it in second bucket. If it's between 2.66 billion and 4 billion, then I'll put it in third bucket. So what do you expect the first bucket size to be full of? Now how many elements do you expect in the first bucket? 1.33 billion. 1.33 billion, exactly, right? If it's less than that, that means you have at least one missing element there. So now your question reduces to, with 3 buckets, 3 numbers, how do I find all the numbers between 0 to 1.33 billion? So any number that's outside 0 to 1.33 billion range, I ignore, I don't even look at it. Now I go divided by, again 3. So whatever is 1.33 billion divided by 3, 1/3, 2/3 and full. Again 3 buckets. Then I know whether it's in the left half, middle or the right half, right part, right? And then based on that I can rezone my range. So this is, okay? So the goal here is to identify what you need to filter out and what you need to divide. And how do you need to put in the bucket. That's like a 2-step process. So this question is actually more complicated, less complicated than it actually sounds. I mean, there's nothing fancy here. All you need to do is to look at how do you actually, this is all about like counting and figuring out how many elements are there in each of these spots, right?
So this is different than the bit vector solution.
Again?
In the book, this is different than the bit vector solution in the book, right?
The bit vector is the first solution, but if you have 10 megabytes, how do you deal with it? Is this. It's the same core concept and the core principle of that. But if instead of 10 megabytes, what if it's 10 blocks? Then this is how you need to go, right?
The time complexity for this one divided by 3:1. So
What is the time complexity?
So that is difficult to say. It's definitely above n. But,
No, this is actually pretty straightforward to say, right? So how many iterations do you need to find the answer?
First we iterate all elements,
And
assuming that it's in the third range.
No, you need log n iterations. Always. Like
we
log
need
whatever the
log of how many numbers based on
Based
what's the
on
bucket
base
size.
case, right?
Base number of blocks.
No, but those are number of iterations.
How many iterations do you need? Tell me that first.
Yeah, log n to the base 3.
Whatever the k is the size that I have, right? If k is finite, which is like 3 or 4 or 5 or 6 or something that's a finite number, then how do you convert from log to the base k to any other log base? You just multiply by log of k1 by k2, right? That's all. So that's also a constant number. So log, if I say that your algorithm is log 10 to the base n or log e to the base n or log 2 to the base n, right? It's all log n. That the base doesn't matter as long as it's a finite number. Okay? Unless you say, it's like if you say what's log n by 2 and n, right? That makes a difference. Unless the space, if the space that you have is constant, then it is log n. The number of iterations that you need, right? This horizontal iterations is actually log n. Clear?
But that is number of iterations.
But to find out those numbers,
Number of iterations is log n. For each iteration, how many times are you going through the entire array?
One.
Right? That's n elements there. So it's n log n.
Yeah, no, but then the next time n plus n by 3 plus n by 6.
No. You still have to go through all the elements.
It's not sorted.
Oh, yeah. Okay.
You don't have any choice, but you go through all the n elements. With each element, you decide whether I am ignoring it because it's falling outside my filter range, or I'm considering it and I'm dividing it into which bucket it falls, and then I'm using it to add. Right?
So that's again n many times. Right?
Every time it's n, and I do it log n times. So this is n log n. So pretty straightforward. I don't think it's complicated. Anyone who disagrees with n log n, we can actually just walk through that and take it. I can go through that again if required. Okay, it's pretty straightforward. Now, what happens if I actually tell you that that you have like 10% of the space available? Like if your space is like billion numbers, I say that you have space to store 1,000,000. Or if the space is like, I don't know, heptillion, septillion, whatever, you have like 10% space available. You don't have space for everything, you only have 10% space available. Now what's the time complexity for this?
It's the same.
10 iterations.
It's the same.
So n log n?
10 and something.
How many iterations will you need if I give you 1,000,000 numbers already? I give you like to find 1,000,000,000 numbers, and I give you 1,000,000 buckets. Right? How many iterations will you need?
So yeah, log n. That's constant.
Why is it log n?
No, but 1 billion you said, right?
I have 1,000,000 numbers. Right? In this case, I didn't say 10%. I said 1. I'm saying 0.1%. Okay. So I'm saying that I have 1,000,000 buckets available for a 1 billion number space. If I had this, how many iterations do you need?
10 times 10.
2. The first iteration will tell you all the only range you're trying to disaggregate. The first iteration is 0 to 100. I can divide it into 1,000 buckets, right? Into like each bucket of size 1,000. I can divide it into 1,000,000 buckets of size 1,000. I know which bucket is actually missing.
Yeah.
Correct? So in 2 iterations I can figure out, correct? First iteration I can figure out which bucket of 1,000 actually has the data missing. In the second iteration I can actually figure out what it is, because that is, since it's 1,000, I can actually go either I can go linearly, or I can actually just use I have 1,000,000 spaces, but I'm only going to use 1,000 and I can figure out. Right? Nothing more complicated. There's 2 steps I can do. Correct? And for each of the 2 iterations I have to go through the billion numbers anyways. Correct? So what is the time complexity?
N.
How did you find out which bucket is actually having the missing number?
So you said you have 1,000,000 buckets. So in the first iteration you got to know one of those buckets, then linear.
How did you figure that out? How did you figure out that bucket 17 is the one that has one number missing?
Because that would not have that particular range that you're expecting.
Correct. But how did you figure that out that it's bucket 17? Like how did you figure out that bucket 0 has 1,000, bucket 1 has 1,000? Because that's not finite anymore, right? In this case it's only 10.
Yeah.
So figuring out that 8th one is the one that's missing and 1 through 7 is not missing is a linear, it's a O of 1 operation because it's only 10 items.
No, but go through the all you have to go through those 1 million partitions. That's okay, but we are already saying that it's n is 1 billion, right?
So n is 1 billion.
Yeah.
Okay, with 0.1%, that essentially is 1 million. So I have 1 million buckets. Each of the bucket has a number between either 0 and 1,000, right? That's what it is.
Yeah.
Bucket 1, 1,000. Bucket 2, 1,000. Bucket 456 has only 900. How am I supposed to find out which is the first bucket that actually has a number less than 1,000?
But I'm keeping track of the count, right, in each of the buckets.
All I have is an array of a billion.
Right, I have
million.
to visit that array. So
And what is our time complexity visiting that?
It's less than O of n, right? It's O of n, but n is 1 million in this case. But overall time complexity we are saying is O of n, where n is 1 million. So it just sums up, right?
So your time complexity is, first is n, which is to go through the whole thing. Then it is plus
m. Yeah, 0.1%.
Then plus
constant 1000.
one more time. Because I have to go through again, right?
All done.
I have to go through the whole loop again.
Yeah,
To figure out that is.
Yeah.
Okay? Which is what? So 2.001 n or something like that, which is again constant.
N, right? Why is it 0.1%? It's 10% is what you said.
0.1. I made million and billion, so that's why 0.1%. The 10% is will work the same way. If it's 10%, then the number of elements you have in each bucket is only 10 in that case. Since I reduced it, it's fine. So now, the thing to notice, despite the fact that you've got like a million buckets, and you have to go figure out, you still have to go through that. That is one linear operation you have to do. Still O of n, so it's essentially O of not 3n, but it's O of 2.001n. Still O of n, right? Anyway, so the point to note was that in the previous scenario, you had this as constant, so you were not even counting that cost. Here it's not constant anymore. So as you change your paradigm of what k is, what n is, you need to start rethinking about how how you would actually store. It depends on how you store the data, and depends on how what is expected of you. Okay. All right.
So on the second pass, you still need another 0.1% of n, like find the number.
The second pass.
Yeah.
What do we do? We don't need. So in the second pass, we only need 1,000 buckets.
Oh, I see. That's
You can just directly do 1,000 buckets and done.
Can be considered a constant.
Yeah, it is. So which will be a constant, and then I just have to go look at which bucket is there. So. Okay. All right. So this one is the next question. This is a question that I like the way this is kind of shaped up. So this question is essentially you're given an array of a stream of numbers, and at any point of time I want to actually talk about get me the rank of it. So let's not do that question. Let's do a slightly different question and then see if we can apply that question to this. So the question that I want to do was, I've given you an array of numbers like 5, 7, 2, 1, 9, and say 6. Okay? I want you to return a corresponding array that actually, for every element, it needs to tell me how many numbers are smaller than this number to the right. Not equal, smaller to the right. So in this case, let me also add something that's equal, just for the heck of it. Okay? So what is the answer for this? 2. What's the answer for this? 2. Same 2, right? Answer for this?
1. 0. 1. 0.
That's all I want. How do I do that? Have you seen this question before?
Yeah.
Yes? Some of you maybe? Okay. This is not an easy question. This is a pure problem solving question. And actually look, and we will talk about
the thing like 9 should be 0 and 6 should be 1.
no numbers smaller to the right. So how many numbers are smaller than 9 to the right of 9?
Oh.
Okay. So 6 is smaller than 9, right?
Yeah.
And it's to the right. So that's what it is. Any thoughts?
So first thing is you start with the right only, because that is first one we can find always 0. And then when you got the second number, start looking at the right. We have to go through everything.
That's good.
So if we take a stack and then start inserting the element from the back and then keep
What do you use? Stack.
stack, yeah.
Okay.
And then insert the element from back, like insert 6. So there'll be a min value, and then we have 9. So we know that 9 is greater than the 6, which is my first number. So I make that, for 9 I make a count as 1. And then I go to 1. So 1 is smaller than 9.
Hang in there.
Something similar.
You had a thought.
No, so initially I was just stating the proof.
So here's what it is, right? So good insight on it doesn't matter, like when I'm trying to process data for this, it doesn't matter whether there's a 1 here or a million here, it doesn't matter, right? And it doesn't even matter how many elements are there before me. All I care about is the number of elements that are to my right. So it doesn't really matter. So I can start from the right side and build this way. So usually in terms of, when you want to figure out bottom up, top down, how do I actually start looking at something? So start figuring out if I can build it incrementally. And that is one. Second thing is that I have to start memorizing or memoizing some data so that I don't know how to repeatedly compute this information. So that's what I want to do, okay? So if I had a way, somehow so for 6 the answer is 0, that's clear, no questions, right? Now at this point of time, I need to somehow keep track of the fact that there was a 6 before me, okay? And knowing that 6, I know that it's 1. When it comes to 1, I need to somehow keep track of 6 and 9 in a sorted fashion. I need to keep a sorted array somehow, so that 1, now looking at 1, how many elements in this list, which is everything to my right, how many elements are greater than, less than me? Nothing, so that's 0. Now I need to have 1, 6 and 9 somehow in a sorted fashion. If I did, right? Okay, so if I did it 1, 6 and 9, then I can find out the location using what? Like if I didn't keep it in a sorted fashion, then I'm going to have to go through everything to go figure out the value, which is n square.
Yeah.
So if somehow I had a magic way of like keeping it in a sorted fashion, then what do I get? Then I can binary search it, which is log n, and that will get me the value of 1, because I know that 1 element is less than me, say 2 elements are greater than me. I can do that. And here it's 1, 2, 6 and 9, and I know that 2 elements are less than me, and then this would be 1, 2, 5, 6, 9, and then it does that. So I can do this, right? But what's the problem here? That maintaining an array is going to be a pain, right? So can I think of a way by which I can have something that lets me, in equivalent of a binary search in a sorted array, a data structure that can actually give me a good lookup complexity of log n, and has the ability to insert elements into it so that the sorted property is maintained.
We can have a binary search tree.
How do you get a binary search tree? Because the requirements of what I want, the data structures, is like so, right? So now, clearly, if I maintain this as a binary search tree, then I don't have to maintain the array, right? I just have to maintain the binary search tree. And binary search tree is pretty low maintenance.
Yeah,
And you get like
node
out of like the element which are like.
So we'll come to that in a second.
Yeah, I mean, the same thing I was trying to say, that we have to keep the track of count in the node, saying that how many are smaller than me.
So the one problem with binary search tree is that binary search tree does not tell me how many elements are less than me. The array gives me that benefit, right? Because the array's index gives me that. The binary search tree's advantage is that it lets me insert. But then binary search tree's disadvantage is that it doesn't tell me my index or my location in the sorted array. So how do I compensate for that?
We can maintain a variable while inserting.
So what you need to do is you need to add a binary search. This binary search tree, so start 6 is the loop, the top of the loop, 9 goes here, and 1 comes here, 2 goes here, 5 goes
Right up as 2, right up as 2. Yeah.
and the other 5, I'm going to say right, left is equal, right is greater always. So that's my binary tree in this case, right? And so one of the things that you want to do is that now when I want to search for this 5, right? When I want to search for this 5, how many elements are there? My goal is to find the number of elements less than me. So if I ever go left, I don't care about the number of elements in the right. I don't care about how many, even if there are a million elements on this side of the queue, it doesn't affect me. So let's assume that there was a 95 here. That was the first element before this, right? What's the answer? 1, 2, 3, 4, 5, 6, right? That will be the case. Now, what I need to do is, if I go, since 96 is greater than 6, I'm going this way, which means I know that this one element is definitely smaller than me on my right. But I also need to know how many elements are here, because I am not going to look at them. And that number is 3, and I need to store that number here somewhere, saying how many elements are actually on your left check. Somehow keep that stored as well. And you can keep updating that as you go, because when you're trying to insert something here, you know that you will insert it somewhere in this tree. So you can increment this as you go. How did you increment this 3? It was 0 to begin with. When you added the 1, you made this 1. When you added the 2, you made this 2. When you added the 5, you made this 3. And actually you added this 5 as well, right? So then you made it 4. So there are 4 elements in this tree, and this element itself is the 5th element, so there are 5 elements that are less than me already, and I've gone this way. Now if I'm going this way trying to insert, so which means I need to add this element as well. So that gives me the answer of 6. So you can bookkeep how many elements are there in my left tree every time. You could potentially also add one more to that value and include the current one as well and call it like not just the left tree but including the left tree, including the root itself. That makes it easier. Go ahead.
This is not, this is still n square, right?
Not yet, but go on. Not yet, but go on. Why do you say it's n square?
Binary search tree, if it's a sorted array, then it's...
So worst case complexity. In a typical, if it's a binary search tree, our notional binary search tree complexity is log n lookup. We have not spent any extra cost. So if you have a properly balanced binary search tree, then it should be log n.
But if you make a properly balanced binary search tree, then you can no longer accurately keep track of what is on the left, what is on the right, right?
A typical binary search tree, if the data set is properly distributed and it happens to be a typical division, it's not exactly a perfectly balanced binary search tree, but it's a binary search tree, then you got the log n answer. Now let me answer a specific question. A specific question is, but if the array was to be sorted, like if it's 1, 2, 3, 4, 5, 6, 7 and so on, then what I'll get is a linked list. It's a tree, right? Can you think of a structure which can help you maintain a binary search tree, which can actually also, while maintaining the property of binary search tree, can also maintain the depth in a reasonable, meaningful way, prevent you from having a lopsided binary search tree. The red black tree, AVL tree would work.
But then this idea of ours that we use this augmentation that how many are on the left, that is something we are maintaining at a property level for each node, right?
Are we? What happens? What happens? So let's assume that we have a tree. If I rebalance this, right, does that change this number?
No. But the next time you try to insert anything on the left, so right now, see, you went right, so when you inserted 9, you knew that, okay, there are 4 elements, so you updated your result for the number 9 to be 5 based on whatever was on 6, right? So, so the next time around, if after balancing that tree...
So if I balance this, right, and I have balanced this to, like, say I put a 2, 1, 5 and 5. That's what I did. Okay? Did I not balance it? I did, right?
Yes,
I did. Somewhat balanced, right? So with this, does that change this number?
No. But something which is going into the left.
As a part of your balance, you will actually rewrite this number to say that this has 1, this has 0, this has 0, and this has 1. As a part of your balance, how do you do AVL? You rotate, right? You rotate the elements. As a part of your rotation, you should be able to math out exactly what the correction should be. You should know.
Yeah, you should know. I have not every time.
If you knowing self-balancing binary trees or AVL trees or red-black trees is sort of more advanced than what I'm looking at folks to do here. But if you know what that is, and if you want to actually use a self-balancing tree, you should be able to implement this, the keeping track of the counts as a part of the self-balancing tree, so that the property is still preserved.
Why do we go for a balancing in the first place? Because the tree can grow.
Because if the input was a sorted array, reverse sorted array or sorted array, then as you insert, right, it will become a long list and it's an n square at that point of time. So that's why you can use a self-balancing.
No, but once we update those numbers, then that changes our...
Do you understand how AVL work?
Yeah.
So when you do the rotate, can you actually, for the rotate, can you redo the numbers so that the numbers make sense?
We can redo the numbers. But once we redo the numbers and the next insertion comes into that area, then the updated numbers don't actually reflect what the numbers were supposed to be.
When I say you redo the numbers, that means you're updating the numbers to reflect the reality, right? As long as you can do that. Can you do that? Like forget insert new. Now that I have done this, right? So you start with the tree. Let's assume that you start with a tree which is like this. Okay? And everything has 0 in it, right? Now if I not the AVL example, but if I convert this to a balanced tree, a fully balanced tree at this point of time, then that will essentially be like this, right? Something like that. Something like this. At this point of time, I expect the numbers to be cooked right. So I expect to see a 2 here, I expect to see a 0 here, a 0 here. I expect to see a 1 here, 0 here, and a 0 here. So once you move from this to this is not what you do in an AVL. If I have a stupid tree like this, and if I convert it to a regular tree, I expect the output to be this. After everything is all right and perfect values in all the locations, then the insertion should not matter. Do you agree with me on that? Yes or no?
So from this, how will we say how many numbers to my right are lesser than me?
We can't do that. From this, you can't go to this. You cannot go from this to this. But in AVL, what happens is you have a mostly balanced binary tree, and from that you go to a better balanced binary tree. Okay? So I'm giving a stupid example, so this is not how it will work. Without actually walking through the examples of AVL, it will be harder, so I don't want to do that now. But if you actually have a stupid tree like this, and you convert it to a better tree like this, and you're able to write the numbers like this, do you see a problem with the output? How to get here is a different question. Let's talk about that later. Will it still work? If I convert, if you're able to use this to solve your problem, instead of this tree, if I give you this tree, it will still solve the same problem, correct?
Yeah, so how will you say how many numbers to my right?
We'll come to that.
If we are not talking about new insertions, then I agree. Yeah.
No, this is new insertions. Right now, okay, give me a number. Give me a number.
0.
0, right? So if I have to insert 0 in this one, do I go left or
That is
right?
not there. We have to insert into this one, right?
2 trees. I'm going to give you both. If I put 0 here, how many do I go left or right?
Left.
Left. Okay, I insert 0, and there is nothing in this binary search tree that's greater than 0. Okay. Now in this tree, 0. Do I go left or right? 1. Do I go left or right? Still my answer is 0. I got the same result by inserting it here and here. So
But-
give me a number.
Yeah, when we insert it, we have to update the count of 1 and 3 also.
Updated in both the places, right?
Count of my left side 1 and
Sorry.
3.
One
Yeah.
also-
I would do this as, thank you.
Yeah.
And has insertion then?
I would have done that. As a part of this insert, I would have done that. Okay? So this is how I'll do it. This is how I'll keep track of it. So now, both these trees are equivalent at this point of time. Give me a different number.
No, but see, okay, so 0 when you fed it in, so that it turned out we did not need any rotation or balancing after.
No, I'm not doing any balancing at this point of time. All I'm telling you is that this tree is the same as this tree. Any concerns? One tree offers better leverage because it's actually well balanced. One tree is stupid, so it's not going to be leverage. This might be an n square. If I have a stupid setup like this, it will be an n square. So work with me here. So this tree, regardless of what number, like if you want to insert a 3, a 5, or a 17, both the trees will give you the same data output. Correct? Like if you at some point of time in an array, you have like a sequence of numbers which resulted in this tree. Okay? Or you had a different sequence of numbers that resulted in this tree. The new numbers that are on this side should not have any bearing, right? The output should be the same. And that will be for this. So far with me? Now, the leap I want you to make, which you'll probably see if you know AVLs better, is that as a part of the AVL rotation, where you only rotate the 3 elements, right? You rotate only a part of it. You should be able to rotate it and keep the numbers in sync. You should be able to edit the numbers right at that one singular rotation and still keep everything in sync. Because the fact that you are trying to balance this or you're doing something to this does not change this number. Does not change this number, any numbers here. The fact that you're trying to balance this tree should not change any of this. The change is very localized. So in AVL, when you balance a tree, you're balancing only a small portion of it. And that should have no bearing on anything else above that. That's the whole purpose of it, right? Because one of the premise that you have is that you are only manipulating numbers which are all less than me. And all the numbers less than me are to my left. So the count should not change, so I shouldn't be having to update anything else. So the challenge for you is to actually implement an AVL which actually maintains the number of elements in my left child and keep that honest every time. And the hypothesis or the expectation is that you should be able to do that without modifying the AVL algorithm significantly. If you know how to do AVLs, you should know how to do this. Okay? So that was the, so in the AVL, like the balancing binary tree concept, you don't go from a completely unbalanced binary tree to a completely balanced tree. That's not what you do. You go from a mostly balanced tree to a slightly better balanced tree by doing like one operation or more operations at a time. So that, if you know that algorithm, you should be able to adapt that algorithm to just keep track of the counts.
I got asked this question about a year ago on a telephonic interview.
Mhm.
How do you do all this in telephone? Like
I can't jump into the minds of the interviewer, but I would have actually probably gone ahead with making the correct assumptions around. I would have probably talked about a tree and I would have left it at that, binary tree. And if the question is like, hey, but binary tree can be bad, what do you do? Like, I think there are other that's more complex, but we can definitely do it. I don't know enough about AVL, so I know about AVS and I can tell you how to do that. But I think we need a shared screen or something because it's a tad bit complex. But if you know what AVLs are, you know I know AVLs. So you can actually give them enough information that the interviewer is comfortable with your knowledge of AVLs, right? So the book for this question actually is using the same thing. It's asking for, what you're asked is essentially, you're given a stream of numbers and you just want to get the rank. Rank is essentially the number in a sorted array. That's all you're looking for. Like in a rank, right? There are n number of elements that are less than v, is what rank means. So that's what you're trying to do. And the solution is identical. And the book actually talks through has the implementation for the AVL, which actually does this counting. So you can look at the book and walk through that. If you don't know what that how specifically it works, then this is it. It's more complicated than what I've normally seen. I have never ever yet seen red black trees being asked in an interview in any meaningful way, unless the candidate actually volunteers it and then the interviewer wants to say, tell me what it is, let's look at this figure out. I don't think it has ever, like there's been no interview that I know of where the solution depends on that. Like even dynamic programming, knowing specific parts of it, I don't think is, like I've not seen any interviews where they're looking for very specialized algorithm knowledge. Like you should know Dijkstra to solve this, right? Has never happened. So questions are there, answers are there. Dijkstra is the most optimal solution, but you could do other things. You could do n square, n cube, whatever algorithm that works for you, and as long as you can solve through that, it's fine. There's no expectation of people knowing that, right? So what I'll do is I'll stop here, but I think I'll take more questions. I'm gonna just hit the record button on that thing. Record. Red button on the back, on the back surface.
Oh yeah.